test. Τέσσερα. Okay. Σε παίρνω.
Σε παίρνεις. Κάνει οδηγούσα, γι' αυτό δεν το σηκώνω.
Έτοιμος. Ένιδες, εδώ, αυτό.
Ρημάρεις κιόλας.
Τώρα.
Ναι. Δεν πάω πάνω όλο.
Αυτό σου μπήκα, τι το
Δεν ήμουν στη μηχανή.
γιατί είσαι, δεν μπορούσα να σου πει κάτι σπίτι.
Δεν μπορούσα, αλλά δεν κάτσα να πάω, μπορεί κάτι να χρειαστεί.
Όχι, τέλος τώρα, εντάξει, είπαμε τώρα, εντάξει.
Αλλά εντάξει, καλού κακού είπα να έρθω.
Εγώ
Καθόλου του πήρε. Δεν είναι μόνο.
όχι, ενώ είχαν πει ότι είναι εχθρέ και μου κόβει ευτυχώς και λέω έχει γούστο, άσα να πάω. Κανονικά έχει support. Έχει σήμερα.
Ναι. Κάτσε πολύ να πάω να αλλάξω το ring.
Εγώ εδώ είμαι, αυτή τη στιγμή βλέπουμε όλα. Είναι ο ήχος, ο κομπλέ.
Εντάξει, πάω να το φτιάξω.
Yes, it's possible. It's possible, it's possible. Δεν έχουμε πρόβλημα.
You want to sit somewhere?
No.
Okay.
So this is clean, everything.
Okay. Pour some water now, so I don't have to. How are you?
Fine, how are you?
Fine. Well.
This is the chairman.
I will be hosting the first session, so
Okay, fine.
anything special I want to say about? I am on the.
Can you give me your presentation?
So you want to prepare the
Okay.
file
No, I think it's already in the system.
already?
I think so. That's what the university told me.
Πού είναι, δεν ξέρω ποιο.
Πρέπει να είναι ήδη στον υπολογιστή.
Γιατί,
So,
να σας δείξω. Εγώ έχω αυτό.
That's what the told me.
Στο day 3 τα φτιάξα σήμερα το πρωί, δεν έχει τίποτα μέσα. Ποια μέρα το έδωσε, την πρώτη?
this is empty for today. There is no file for today.
Wow.
Το στείλε κάπου.
Did you send it via email?
I sent an email to Dimitri, yes.
To Dimitri, maybe Dimitri has it.
Ναι,
Of
προφανώς.
course, I hope so. I hope
Let me
so.
ask Dimitri. I will be back in a
Yes,
minute.
okay. They told me, that it was already in the system. I think I should have it on the USB key. I don't have my Mac with here, but
It's possible if you want to...
but Dimitri, I think in the computer, yes.
It's called the Crete T.
So that will give you some time to do that.
Day 3, session here.
And then you
Well,
will have
first.
first stage, so
Yeah, going back to the States, but then 3 or 4 days
What?
later.
10.
Scottish trip.
back and forth, back and forth.
Day 3, you
Yes,
are the first one.
After
Ah.
the
Session
after
3,
the-
day 3.
Yes.
Let's try that.
It's
It's
a
not so
workshop.
But he told me that it was already.
Okay,
okay,
we
so no problem. Yeah, no problem.
I think there once.
Okay, thanks.
Can you...
It was a lovely place.
Uh,
Very nice.
can we open to check if it works?
Absolutely. Good idea.
Τη βρήκατε?
Second day, not third day. Second day.
The δεύτερη
Ah.
The
μέρα.
file, the file
Second
is
day. Yeah.
in the folder of yesterday.
Yes.
Το έβαλε.
Yesterday.
Day 2, ωραία. Σε ποιο session είναι? Το έβαλα εγώ.
Works. Am I projecting? I didn't even look to check it. I was projecting.
Okay.
This is what he told me. He's
Δεν
coming.
τα ψάξα εγώ, δεν
He's coming. He's coming.
Okay, it's working. I see.
Yeah.
You want to duplicate the screen, yeah?
Yeah, absolutely.
Display.
It'll be easiest if I just work
Yeah,
off the
yes.
screen. Okay, you're up. Okay, I see it.
Okay.
Perfect. Sorry? Yeah, I am.
Yes, it's possible if you want. No problem.
Oh, you can download your thing onto mine. She's next. She's second.
Yes, I know.
Okay.
My computer, some keys does not work. Some keys do not work. So I download it.
Yeah, yeah.
Is it download?
It's down there.
Wow, you did it first time. You just learned it from my machine. That's what the 60s.
Ah, okay, I can dig it
it bigger and littler. Thank you. All right. That's actually not where I'll start.
Maestro de music. Maestro de maestro.
Αυτό είναι το session. Εγώ το έχω δει. Τα είχαμε χτες. Day 2. Έτσι τα είχαμε.
Because I saw something different.
Και είναι session. Τι είναι? Όχι, τι είναι? Όχι, τι είναι δεύτερος ομιλητής. Session. Καλά το έχω, το έχω. Είναι day 3. Day 3. Session. Τώρα. Το έχω. Πείτε μου ποιος κύριος είναι. Sure. Yeah, that's first. Αυτός 3. Αν είναι 3. Πρώτος. 3. Okay.
Οπότε βλέπω παίζει να το χρειαστείς αυτό.
Γιατί?
Type-C σε HD κάποιο. Α, έχει.
Πώς παίζει αυτό? Εμάς δεν έχουμε. Αυτό ξεκουμπώνω και βάζω εδώ. Δεν έχει...
Oh, too late.
Makes sense. Yes.
Yeah, I'll download this
Yes.
lecture. I think this is one. The most recent created one. If you arrange the one.
Group.
I think it's called the Vassilios lecture. Oh, that's some restaurant, the Vassilios Dougalis. This one.
Olive.
Yeah.
Olive mint.
Yeah, olive and mint.
Okay. I will try it.
Let's see. Arrange. Yes.
Wait. I will.
It's called the if I
Date
will-
modified.
Date. Date.
Yes.
Oh yeah, that's
Vassilios
it.
Memoriam.
Yeah.
This.
Check, make sure. I can open.
Okay. Wait. Wait.
Yeah, that's it.
That's it. Okay.
So where should I put?
Okay.
Just
I
put
will.
Just on the desktop. this one?
Yes.
Oh, yeah. Okay.
We will check it if.
I think that's this one. You can just eject this one. Should be. Not quite.
Πέρα.
Okay.
And we. Okay, it's working.
Yeah.
Το απλά είναι δικό μου, δεν είναι του Ινστιτούτου, θα μου το δώσεις.
Έτσι, αλλιώς αυτό θα το πάρεις μαζί.
Ποιο?
Αυτό θες.
Ναι, λέω αυτό δεν είναι, ναι.
Δεν βλέπω, μάλλον. Πώς τα έχουν έτσι, μάλλον, σκοπιά. Και πώς θα δουλεύει. Λογικά δουλεύει. Έχουμε τρία κουτιά. Αυτό λέιζερ, το κόκκινο, και δεξιά-αριστερά που είναι η παρουσιάση. Χθες πάτησε κάποιος το μαύρο, αυτό το μαυρίζει την οθόνη. Ήταν το σημείο. Ναι, το θέμα είναι να τρέξουμε μια παρουσίαση, να δούμε αν δουλεύει. Ποια είναι η παρουσίαση δική του?
Να, για στο desktop.
Όχι, δεν θέλω PDF.
Άνοιξε ένα PDF.
Ένα λεπτό. Enter full screen.
Yeah, I know we're trying to see if it
Λέγαμε. Ναι,
Yes.
it works.
So
Yeah,
this
tell
is the laser pointer.
Εντάξει.
Ωραία.
This you go button. So let me welcome everyone to the second day of the conference. 2.5. We start with Professor Jerry Bona. Before I announce the title, let me remind you there'll be a photo opportunity at the end of the morning session right outside this building, so show up. So let's introduce Professor Jerry Bona, who will be talking on KDB over the complex numbers. The title is a little different from what you see on the program, but that's what I. Professor Bona.
Morning. It's a great honor, but not a pleasure, to be speaking in this meeting.
It's okay.
Oh. Okay. All right.
Your mic? No, it's not good. You will reconnect. Okay.
Yeah. Yeah. Okay. Okay. So, let's see. It's May of 1973, and can you hear me? It's May of 1973. Oh, turn it on. Yes. Thank you. May of 1973. Have been invited by Garrett Burkhoff, who was my thesis advisor, to come spend the summer at Harvard, and. I walked into Garrett's office and I met Vassilios Dougalis, who was a young graduate student at the time. And by the way, he was very skinny in those days. So we hit it off somehow right away. I mean, it was somehow magic. And so so I was supposed to be working with Garrett Burkhoff, but actually I spent most of the summer working with Vassilios. And some of what I'm going to talk about, you can, if you understand the details well enough, can trace back to the work that Vassilios and I did in 1973 before he had a PhD. We didn't publish it till much later, but that was my fault, not his. Okay, now, Vassilios was a wonderful man. He's a fine mathematician, and he did great things for Greek applied mathematics. There's no question about that. It was almost non-existent before he got here, and now it's not far from non-existent. But there were other aspects of Vassilios that I held dear. One of them was that we met in Greece many times. We also met as Fokian said in his lecture, in University of Chicago and Penn State, University of Texas. Never managed to get him to come to University of Illinois at Chicago. One of the things that we did in Greece was to travel around Greece, this island and the mainland, and Vassilios would regale me with the history, and he had it at his fingertips. He didn't have to think; it was right there at his fingertips. So, and I was an apt student. I really was happy to listen to him. So I'm going to start my lecture with an example of Professor Dougalis teaching his students. So here we go. No, not that one. Oh, that's the PowerPoint, yes. Why is this PowerPoint not opening up? Oh, there it is. Okay, fine. Full screen. Okay. Okay. Thank you. Okay, fine. So that's the title of the lecture. That has nothing to do with Vassilios. So you'll all recognize that. That's the old agora in Athens. And here's Professor Dougalis and his two eager students about to be shown around the agora in a way that most tourists or not. So here we are getting over to the agora. And there's our first view of it. And now Professor Dougalis holds forth. And it was absolutely wonderful to be in. I was in this kind of situation probably 20 or 30 times.
When is it, Jerry?
Sorry?
What is the picture?
It's the agora.
When?
Oh, when?
2018.
2000, it was at his retirement party. Well, we called it a conference. So you can see his students are hanging on every word. And here we are actually in the agora. In those days, you could just walk in. It wasn't completely fenced in the way it is now. Here's a posed picture. And we're always taught to give credit. My Garrett Berkoff and various advisors that I've had over the years have always said, be sure and give people credit. And what credit did I not give? The photographer. There she is. Okay, so that's just something about Vassili that I adored. There were many things about him that were in that category. Okay, now let me start talking about mathematics. Yeah, it's okay, it's okay. So the work I'm going to discuss feels like it's pure mathematics because it just arises out of nothing. It's not in fact the case. And Johannes, in his lecture, talked about the problem. So I'm not going to use this Blackboard much, but I didn't prepare the relevant slide. So I want to talk about.
Maybe the light should be on, otherwise we cannot see it.
Sorry?
The light should.
Okay, thank you.
So the marker is not perfect.
But it's okay, we can fix it. More or less. More or less. More or less.
It's less.
Yes, you can see whatever. Of course. You
Okay.
less.
All right.
So X plus B will be X.
No, the black.
Black. Okay, fine. Thank you. Okay, so this is a coupled system. This is what Johannes was talking about. Okay, P and Q are quadratic homogeneous polynomials. So U squared plus UV plus V squared with coefficients. So there are 6 coefficients, A, B, C here, and D, E, F there. Why are we studying this system? Well, the equations of this sort have come up in several different physical situations. So Johannes mentioned a couple of them earlier. And so we decided, look, we shouldn't be doing these things one at a time. We should just go ahead and do the whole thing. Okay, so you have P is AU squared plus BUV plus V squared, and similarly for Q. And so we wanted to study the general situation where A, B, C, D, E, F are constants that are specified and see what happens.
You don't want to have a linear term like UX and VX.
No, you don't have a linear term. And of course, it is true that there's no coupling in the dispersive terms, but so long as it's non-singular, you can get rid of the coupling in the dispersive terms with this linear transformation. So this is fairly general. Okay, so there's oh, that's interesting. Okay. Nobody ever wants my picture. So we undertook a study of this, both theoretical and numerical. And we have theory that says that there are certain conditions on A, B, C, D, E, F that imply global well-posedness, and that's sort of actually kind of boring. It just says you've got solutions for the initial value problem. but there are also, that condition doesn't always hold. And so that's actually more interesting, just mathematically, because now you might not have global well posedness. We don't know for sure, but we do, you're going to see we do know. Okay, so there's one, in these numerical simulations, as Johannes mentioned, there are all sorts of instabilities and blow up that we see numerically. One of the ones that that came up and had some odd behavior was the case where A equals 1, B equals 0, C equals -1, D equals 0, E equals 2, I guess, and F is 0. Okay, so why is that one so interesting? Well, if you take a solution of this and you let W be U plus IV, then W satisfies the Korteweg-de Vries equation with complex values. Okay, so then Fred Weissner and I got interested in this particular one. It related to some other work we've been doing. And so we undertook a study of that, and that's what I want to talk about. Okay, took me 10 minutes to get to the topic. All right, how do I make this full screen? Sorry. It's just a PDF file.
Να το γιατί.
It's not so trivial. Thank you. Okay. Okay, so here's the Korteweg-de Vries equation. I put a 2 there because it's just U squared sub x. I'm going to be concerned with the periodic initial value problem. And notice that the U, the solution, is complex valued. Okay, so Korteweg-de Vries over the reals has global solutions, and they can be very smooth or very rough depending on the initial data. Okay, so you're going to see in a minute, small, smooth initial data. Smooth means C infinity with exponential tails, if you'd like them, can blow up in finite time over the complexes. Okay, and I want to discuss this. Okay, so let's consider the class of 2-pi periodic complex valued functions, which are solutions of this complex KdV equation. And that thing, capital star, is the mean value. And that's a very important, it's a number, it's a complex number, and it's very important. Now, I want to start out with some, so the work of Weissner and I is based on the work of Staffelani. I forget exactly, some 20 years ago. So here's her theorem. The KdV over the complexes is locally well posed in the, okay. Actually, her theorem says it's locally well posed in HS for S bigger than -0.5. Her interest was in how low you can go. That's not our interest. So we're going to be happy to be well posed in L2, but notice there's a sub-zero there, and that means mean value 0. Now, why, I mean, when you solve these problems over the reals, you never have to worry about the mean value. You can use a Galilean transformation, and if it's mean value 0, you can make it, if it's mean value non-zero, you can make it mean value 0. Just a simple Galilean transformation will do that for you. That's not the case over the complexes, because the Galilean transformation, if the mean value is complex, you no longer have a function on the real line. So Okay, so Staffelani's theorems, here is the Galilean transformation. Phi bar is the mean value. And if you take that transformation, the V has mean value 0, you apply her theorem, and everything is fine, provided this is real. If this is not real, x plus, the function u is not defined at x plus phi bar t. It's just not a function, not defined for there. Okay, so first question is that important? I mean, is it important that it have mean value 0 or not? Well, if you look at the proof, you will see it's used 2 or 3 times in the proof. The proof uses these Bourgain type estimates and so forth. Okay, so maybe you're just not smart enough. Okay, so let me continue a little bit with the history. There's not much history. Bernier in early part of this century showed that the Weierstrass P function, if you fuss with it a little bit, can be made so that a particular line on that, through that, the period parallelogram, leads to a periodic solution of the Korteweg de Vries equation, and it has, as you remember, there are 3 poles in the P function, and if you organize things properly, one of those poles will cross the real axis, and you'll get a blow up in finite time. By the way, if you read Bernier's paper, you'll struggle to find what I just said. It's there, but you'll struggle. All right, so let's now talk about some function classes I'm going to need. So L2 naught is just the things with mean value 0, L2 function with mean value 0. And L2 plus is the functions which whose Fourier coefficients for k negative are all 0. So only have positive Fourier coefficients. And, okay, sorry, the notation's a bit heavy here. L2 0 plus is the ones where f hat, the Fourier coefficient at wave number k is 0, and this is for all k less than or equal to 0. So that's going to be important. So this function, this class, is in the class that Staffelani's theorem applies to. So it has mean value 0. So okay. Yeah, okay, fine. Okay. By the way, the things I'm going to talk about do not depend on rough data. The data can be as smooth as you like. So the S there is HS. All of these things, all these spaces are over on the torus. And if I had a solution to complex KdV, U of x and t, it would have a Fourier expansion for each t. Right? It's an L2 function, so it has a Fourier expansion. And of course, the AKs, the coefficients, will depend upon t. And they depend continuously on t. Just take the inner product of the solution with e to the ikx, and you'll see that that's the case. You can also write that solution in a de Hammel form, and that's here. Okay. Now that's not so important for what we're talking about today. All right, the central observation, the thing that makes this whole thing go, is here. If you take initial data in this L2 0 plus, remember that's just the initial data which has only non-zero positive Fourier coefficients, 1, 2, 3, but not 0 and negative. Okay. Then that function class is preserved by the flow. That's actually easy to see. You'll see it in a minute, in fact. How do you know that? Well, of course, the 2 linear terms, the ut and the uxxx, don't mix Fourier modes at all. And the u squared, which is the only thing that's left, that also preserves this class. Right? If you have only positive Fourier coefficient and you square it, you still only have positive Fourier coefficients. All right. So that's the observation that makes everything I'm going to say going forward the case. All right, now there's some, I'm not going to go through this. There's some Gavret class analysis that allows you to, okay, so if the general situation is the following. You have an initial value problem, and you have a local well-posedness theory, so that's Staffelani. What can you say without thinking? What you can say is there are two possibilities. What did I do? Better one here. There are two possibilities. You have a maximal solution. So U is continuous with values in, let's say, minus, T minus, comma, T plus, with values in L2 naught plus, like that. And the T minus and T plus are maximal. You get this by just waving your hands. Question that you're interested in right away is, are they finite or are they infinite? If they're finite, then the solution blows up in whatever class you have here at those endpoints. That's always the case. It's a general fact. So the questions, one question that comes to mind immediately is, can these things be finite? That is, do you have blow up in finite time? And by the way, there's nothing magic about L2. This could be HS plus naught. Okay, so same remarks. Okay, so this Gavret class analysis gives us a lower bound on the time of existence. Okay, you get a lower bound. And as I say, I don't want to take you through this. By the way, if you start life in the Gavret class, the solution is C infinity. It's actually analytic. All right. So keep that in mind. And so here's some results that follow from that Gavret class analysis, which I didn't show you. The first theorem is that if you start in L2 0 plus and you take the maximal solution, then either T plus and T minus are both finite or they're both infinite. In other words, you cannot have a situation where it blows up to the left but doesn't blow up to the right. Right? That's not possible. Okay. And the second result, which is maybe surprising, is that T plus plus T minus bigger than 2 pi, then the solution is global. Okay. Where did that come from? Because that's far, far from obvious. All right, a corollary of that theorem, and this is a very simple criterion, is that if you take initial data in HS0 plus, that is positive Fourier coefficient, smooth as you like, and the first coefficient, A1, is larger than 6, the solution blows up in finite time. Okay, so by the way, this is all for mean value 0 stuff, right? We haven't moved away from there yet, we will. Okay, and that 6, 6 has to do with the fact that I scaled KDV with that 2. If you change the scaling, you get a different number. So 6 is sharp in a certain sense, not sharp in the sharpest sense. There are, if you take any gamma in less than 1, and you take a U0, there exists a U0 in this initial data space, such that A1 of 0 is 6 gamma. So that means it's as close to 6 as you like, but it's not quite 6. And the solution is global. Okay, so as I say, the 6 is kind of sharp, not in the strongest end. Okay, now, so that's blow up in finite time. Now, one thing that Staffelani doesn't do in her paper, she doesn't deal with ill-posedness or well-posedness. It's just not there. And there's a reason for that. Here's the reason. So if you give me numbers epsilon positive, that's going to be small. Epsilon's always small, right? And M positive, that's going to be big. T positive, any HS space you want. This is not a result that depends on roughness. Then there exists initial data in HS plus such that there does not exist a solution on C0THS with initial data U0 that is less than or equal to M in HS norm. Okay, so that's a lemma. Oh, I didn't do anything, did I?
You jumped.
What did I do?
Keep data in mind. You jumped. Right.
Oh, yes, okay. Fine, thank you. All right, so that lemma leads to this, what's called a norm inflation result. A norm inflation result is a very strong version of ill-posedness. What it says, okay, you can read what it says, but I'll tell you what it says. It says you can find solutions that are, they exist they're arbitrarily big for arbitrarily small times. That's what that says. Okay, so there's a sequence of solutions. The sequence converges to 0 in HS. So the initial data is getting smaller and smaller, and it's getting larger and larger at smaller and smaller times. So you start the thing off and it's as big as you like in as small a time as you like. That implies ill-posedness, but that's a very strong version of ill-posedness. You know, typical ill-posedness result says something's not continuous at the origin. Okay, now this, how am I doing? Not very well. Now we're going to move to the situation where the mean 0 is dropped. And basically what I'm going to tell you is that Staffelani had to have that condition. Because if you take a U0 in L2 plus, which is not C infinity, that has to do with that Gavre space analysis, and suppose its mean value has non-zero imaginary part. So if the mean value has real imaginary part, you can use that Galilean transformation to solve the problem for any mean value, for that mean value. If you have non-zero mean value, there is no solution, even in the sense of distributions, in C minus TT L2 for any positive T. No matter how small you decide, I just want a solution for a microsecond, there isn't one. So that there's something to understood here, and I don't understand it. But there's some kind of inconsistency here with having a mean value which has a non-zero imaginary part. And one could see that in the numerical simulations of Hongchu and Ohanes. And okay, so how do I do it? I'll tell you in 1 minute. So if you look at that system of equations and you look at the Fourier coefficients, they satisfy that little set of, this is for all k, ak prime minus ik cubed ak, that's just the linear part, plus ik bk. And now you see why it is that you're taking these Fourier coefficients to be all positive, because the bk starts at 1 and ends at k minus 1. So what that says, A1 you can just solve, it's the linear problem. And then for any higher values of k, you just iterate. It's that linear equation, ak prime minus ik cubed ak equals something you know. You can solve this iteratively. That system of equations, of ordinary differential equations, has global solutions, always. And we call those formal solutions. And the question is, when is a formal solution a real solution? And that's what the analysis is all about. Okay, I'm about to go over. I know that the next person is eager to get up here, so I thank you for your attention.
Thank you very much. Any questions for our speaker?
I have a remark. You see, consistent with your results, Jerry, as you know, Bernier, in addition to this global failure that you mentioned for the periodic, he also did analysis for the infinite line problem.
Right.
As you know, and he showed also that you have a failure, and in the sense that this Riemann problem you get doesn't have a symmetry, therefore you have solution. And as I mentioned yesterday, we did the periodic problem with Jonathan Reynolds.
Right, yeah, sure.
For real situation. And again, we rely on reality to prove that this Riemann problem has solution. So I'm sure that without this, we didn't try, but I'm sure without this results, you would have failure.
Well, it would be interesting to see how much of the inverse scattering theory works in the complex plane. I mean, of course, you're working in the complex plane all the time, but this is different.
No, it's of course, completely different. Completely different. No, as I said, you see, the main tool, as you know, for inverse scattering to get global existence, if you want, is that this reality gives you symmetry on the Riemann problem.
Right.
So now you
That's
put
right.
space, and I don't know what one can do, but it's interesting to think about.
Yeah, it's as I say, there's something to be understood here. If you go back to the 50s, there were these early results of, forgotten who, one of the NYU people. They wrote down partial differential equations that had no solutions, none, whatever. And there was a whole little industry for a while in that. And this is maybe another example of that. There's something. There's those equations that they found in the 50s basically were inconsistent. I mean, in a kind of a subtle way, but they were basically inconsistent.
But this is not.
And this one doesn't look inconsistent, but it's still okay.
Very interesting.
Any other questions? So let us thank Professor Dougalis again. And we welcome our next speaker, Hongshu Chen from the University of Memphis, with a talk on the long wavelength limit of periodic solution of water wavelengths.
Thank you, Michael. Okay, thank you. I'm honored to have met Vassilios. So I met Vassilios more than 20. I met Vassilios more than 20 years ago, and I'm honored. I'm honored to be here celebrating his life. So this is what I'm going to talk about. Let me move to the next slide. So this is the background. And if you talk to the numerical analyst, sometimes you ask a question about the solutions. And you ask what kind of domain you are using. Many of them would say using periodic data. So, and the question is, if the data of the solution is localized on the infinite domain, how are you going to do the numerical solution? So this is what I like to address. And use periodic solution to approximate a localized solution on the infinite domain. So this is a background for a few decades. And so normally that's what people do, however, no rigorous theory. So this is what I'm going to address. So I'd like to start with some problem which is simple, really simple. You can calculate by hand easily. And then you get the idea and you can move on to more general solutions. So I start with this regularized long wave equation, or what we call BBM equation. So this is the equation. If you notice, the space variable is on the entire line, and this is initial data. We just play around. This is standard way to do. We can convert this differential equation to the integral equation, and this is the integral kernel K, and the K can be found directly if you have good background with Fourier analysis. This is easy to find. If you don't, if you're just undergraduate students with baby PDE class, you can find this kernel as well. So this is from standard textbook for PDE. So this here, now what I like here, since the solution is localized, I like to address and the issue related to periodic data. If the initial data is in H1 space, now the underlying space is entire line, and this is an old result. The problem is globally well posed. It preserves the H1 norm. So that is an ancient result. Here, the more recent result, probably 10-year-old, and if moreover, the initial data decays exponentially. So somehow this solution, if you look at this estimate, and in terms of space variable, it decays exponentially. However, and in terms of time, this grows. That's what we can estimate. However, this is a number, it can calculate straightforward. So this is the background. And this proof is quite simple. And basically just use Green-Y inequality, use a little bit older term, here, use this transformation. You can estimate V, then you can get the U. So here, this is just tedious integral calculation. And this, we got this result. And as soon as we get V, its maximum value is bounded by this number times exponential function, and now get back to original function U, we get this estimate. So this is a kind of a preparation. Now, I'm going to talk about the periodic data. So this is well known. If the initial data is a periodic function, so is the solution. Now, there are some different issues we handled before. This time, I'm going to do differently. So I'm going to find out the integral kernel for the periodic data. Just play with mathematics and write this integral over 9 toward infinite series. Now, we play with this integral kernel, and using Poisson's summation formula, we can estimate, and we can write down precisely. If we deal with periodic data, so the space variable x is between -L and the positive L. Now the issue, if you now glance this interesting direction, this periodic integral kernel and the original kernel on line differed by this exponentially decay function. Now the period, half period occurs right here. So this one you will see they kept the same regularity, differ by very small number. You can call the periodic data is original function perturbed by some exponential decay function. So we get back to this problem, and you can work on the global well-posed list and well-posed list easily. So here, this is this data mimic to the problem we just handled before. So here, if you only work on this problem, it's trivial, it's low interesting. However, it's associated with a comparison. If the initial data is periodic, and it's with a regularity 1 on this space, both phi and its derivative are L2 function on this periodical interval. And of course, here, this is trivial to prove. And if this function phi is in H1, automatically it's a continuous function. This automatically true, or this data is true. So here, and this is automatically true. Of course, if you talk about the limit as L tends to infinity, you see the picture of approximation of the connection of two functions. And this is similarity of estimate. So here, now, the interesting part is about the comparison. So before I talk about the comparison, I just play. Suppose we have a localized function on none in H1 space. So this periodic function with the same regularity, but it's periodical, and with a period 2L. And now suppose there's a lambda, this is same. So this is a requirement. This is automatically true for here. At this one, if I'm not talking about as L tends to infinity, this second part is automatically true. This leads to requirement. Now we do a little bit of tedious work. We got the comparison of these two functions over interval from minus L to positive L. It's bounded by this maximum value of the difference of a periodical function and the function, localized function. Now if you notice this tail left over is constant, C1 times E2 minus lambda times L. This exponential function e to C2 to T. Now the question is, somehow if this initial data, the difference of two initial data restricted on the interval from minus L to L, centered the origin. If this is a small as the same order as this part, you can see, whatever time interval you want, you can choose corresponding length of periodical interval, such that these two solutions are very close. So the next issue, if you generally draw a graph, you can always say you can approximate this solution. But however, if you want these two solutions are very close in terms of this exponential estimate, then you need a requirement. So this is a conclusion. So this is kind of a simple estimate, and the use of Poisson's is similar. If this localized function, I call phi sub infinity over entire line, is exponentially decay, then we can also choose periodic function with the same regularity as the original function. This can be chosen if we relate limit on interval centered at origin with a period 2L. We can also find this estimate, and this C2 can be represented explicitly in terms of L and lambda. So it's explicit. Then you can have this estimate. The solution, the difference of two solutions, localized solution and the periodic solution, limited on this interval, is bounded by a constant C1, and you can calculate precisely times this exponential form, decay exponentially in terms of space, grow in terms of T. So here you play with this one. If you want these two solutions are close within given time interval, you choose L sufficiently large and vice versa. So this is the background. That's a prelude. I also teach my students, if you want to do some completed problem, start with a warm-up problem and get to your goal. The goal is about this equation. So this equation was derived by Bonner, Carvalho, Panfi, and Shalom, and these three people are Brazilians. And they developed this model equation years ago. This is a higher order approximation of a water wave problem relative to KdV equation over BBM equation. Here, beta is associated with dispersion. Alpha is associated with the nonlinearity. So here they have a physics million. If you think about alpha and beta are very small, however, they are same amplitude, the same magnitude. If you drop this quadratic term of alpha and beta, you get back to the BBM and KdV equation. So, and if you keep them, you get the higher order approximation of water wave model equation. So, and it was a very long modeling paper. And also they showed the well-postless, local and global well-postless problem for this one. And later, Jerry and Colette Giope, we improved the result and use some simpler method to get the stronger result. So that's not the issue here. Now, here the issue is, if you look back, this dispersion has a fourth order derivative mixed with x and t, together with fifth order derivative with pure x. This term is not very nice. It's hard to handle. However, the trick with Jerry and Colette we did is make a variable change. We make another variable change, we can get rid of this fifth order derivative with respect to just x. Now this problem looks much neater, much easier to handle, and all the change get back to the original data. So now from here, we work on this initial value problem. Again, standard way to change this differential equation to integral equation. So regroup and put the dispersion term to the left, and with derivative with respect to t, and the rest term to the right hand side. So we invert this operator, we get this equation. We get this integral equation, and the k, we get the nonlinear term for the first integral here, and the second integral, and the issue is collect for second one, we have a k, it's easier to play about the well-postless. Here now, do a little bit calculation, the integral kernel can be calculated in terms of three categories. And this looks more complicated, but underneath the concept is the same as BBM equation. So here, also interesting issue is, if you look at all this integral, all three types of integral kernel, they are all exponentially decay in terms of space variable of x. Theta and rho and their numbers can be calculated explicitly. So here, there's a second order derivative of the integral kernel. So here, that's important. What I like to emphasize, exponentially decay integral kernel. So this is a number you can calculate. So here, this is just what I said about the global well-posted, local and global well-postlets. We improved with Jerry and Colette. So here again, now get back to the periodic data. So here use the same idea from the BBMA equation. So this problem, oops, this should be minus L to L. This should be, this is a typo. This should be minus L to L. So here, this periodic integral kernel can be calculated. This is a calculation, and basically just a geometric series. And in the third category, you have imaginary part. So here, this kx can be written in this representation. It depends on the sum of x. And this is a number in the denominator, and the difference of two exponential functions. Rho 1 and rho 2 are explicit. So similarly, now following the same idea, and if you do abstract calculation, and you can get the same result. Here, instead of a continuous function space, this is the C1 space, because we need the first order derivative. So this one, the maximum value, the difference of the maximum value of a difference of these two functions over this space interval is bounded by, again, similar to what we did before, exponential function in terms of space, exponential decay, and exponential growth in terms of space, in terms of time. However, there is an initial data. So the general idea is, if two functions phi sub infinity and phi sub L are very close, these solutions are very close. Of course, this you can do the abstract, and if this closeness can match to this closeness, and the estimate is much easier. So here, just same as what we did. So if this is true, the issue becomes, if this localized function is given, how are we going to choose this periodic function which is close to this function over its space interval? So that's another issue. So, oops, I thought I have one more slide. Seems here, in fact, this is true. If the periodic, if the original localized function is in this space, and then we can choose and this one decays exponentially. We can choose corresponding this periodical function in a very explicit way, such that this is in the same order of magnitude as this one, which means we play around for any time period. You can choose a sufficiently large time period, make right-hand side sufficiently small, and vice versa. If you have if you want this small for some period length, then you can get a certain time interval, get this small. And with this estimate, you can do either way, and it depends on your goal. So this is a theoretical estimate of two solutions. One is on the infinite domain, other is on the periodic domain. So this is the answer for some questions and in my mind for many years. Also, after this work, you can get back. Let's see. Let's here. If you look at this problem online, if you generalize this problem as long as a problem differential equation can be converted to integral equation. If the integral kernel decays exponentially, this method works. So this general idea starts with a very elementary calculation to a more complicated application, and they get to more general case for differential equation. So this is the end of my talk. Thank you.
Any questions?
Yes, Andrew?
Is there any way to estimate this constant C2?
Yes, there is a precise formula.
Okay.
Yeah, it's precise. Of course, it's upper bound, but you can estimate it's upper bound, but
Is
it's
it large
constant.
or small, or how?
It's actually, it depends on the 1 over 1 minus lambda, and it depends on the initial data linearly. Yeah, it depends on these two initial data, localized function and the globe and the periodic linearly. Also, in fact, if you choose the period is sufficiently large, the periodic data is very close to localized data. And it be just almost equal, not quite equal, with a little bit multiple, but almost equal. If L choose sufficiently large, you can estimate it precisely. And the C1, C2, it's explicit. That's good for the numerical simulation, right?
Yeah.
Yes, that's the purpose. You can calculate the numbers and the upper bound precisely. That's why the probably numerical people might be interested. Yeah.
Any other questions? If not, let us thank Professor Chen once more.
Just kill it, right?
No, I'll
Give it to Jerry.
θα χρησιμοποιήσουμε το άλλο τώρα. Up to you. It's fine, perfect. Thank you very much. Okay, just okay, fine. Okay, this,
Right, let's
okay,
end the
good,
lectures.
good.
Let's just go in the talk.
Yeah, perfect. Thank you.
All right. So, the third speaker for this session is Professor Jean-Pierre Shaw, with a talk on the Bussinet and Bussinet-like systems.
Okay, so thank you. So let me first say some word on Vassili. So I met Vassili in the 90s, I think, and then we had 3 joint papers with Dimitri. And after that, we became good friends. So we met in Athens, Crete, and Orsay. We used to spend vacation in Crete. So Tina and Vassili were in Rodakino, and we were in Plakias, which is nearby. So we had a very nice dinner there, talking about children, grandchildren. And I must add that Vassili was a great scientist, but he was also a man of great culture. I was impressed by his knowledge of French literature, for instance. He knew Balzac more than most of French people. Okay, let me just start by some pictures of Vassili, pictures in Poros, in Athens, and Orsay. So this one is in, I think, in Poros, which was in, when we are visiting this island with Tina and Vassili. This was in Orsay in 2007, I think, a long time ago. So this one with a famous mathematician in Orsay, same time. This one is in Vassilios' office in Athens. This one is Tina and Vassili in Poros, I think. And this one, I like this one because it's in front of Seferi's house, Villa Galini in Poros. So Vassili and I were very fan of Seferis. I was very pleased to see this famous villa, this picture of villa. And again, this is just going back to Peleas. Okay, so what to motivate the topic of my talk? Vassilios wrote about 20 papers on the numerics and theory of Boussinesq system. Many of them were people in the audience, including Dimitri, for instance. So the aim of this talk is to give a brief survey of what is known and what is open on this topic. I will see that to plethora new issues. And I will start from some kind of small histories of this kind of system, of the modeling of water waves. So the story starts a long time ago by Lagrange. So Lagrange was looking for he was trying to have a model for water with free surface, which are not. And so he has the idea to first to write what is called the water wave system. I mean Euler with free boundary. Okay, well, he did it very. And then he discovered that this system was very complicated, as you know, and it was impossible for him to derive some practical consequences. Okay, so he has the wonderful idea to derive an asymptotic simplest model, which can be used to describe real waves. And what he did in modern terms was to consider the linear infinite long wave limit of this water wave system, and he derived this linear wave equation with the correct velocity, which sometimes is called the Lagrange velocity, square root for gh, h is the f of the fluid. It's a fantastic paper. I mean, the idea of deriving a asymptotic model was very original at that time. It was just the beginning of PDEs, And so, well, it took one century for when Boussinesq, improving Lagrange approach, introduced at the same level nonlinear and dispersive effects. Okay, and he derived a system. So the system 1 is in Boussinesq notation, and 2 is in modern term. So zeta is the direction of the wave, and v is kind of velocity. So epsilon it's a small parameter representing the nonlinear effect, and mu represents the dispersive effect. So if you take mu equals 0, you get the so-called Savenor system. Savenor derived it a few years before. Savenor was Boussinesq's mentor. Unfortunately, the system is linearly imposed, so it cannot be of any use to describe real waves. Okay. So actually, just a digression. So in another paper, Boussinesq derived the so-called Korteweg-de Vries equation, much before Korteweg and de Vries, and actually he did much more. I mean, he did. I will translate this wonderful blue quotation. So what he did essentially, he realized that first he was able to compute the conserved quantities of the KdV equation. So, and what he did, in modern terms, he said that the solitary wave minimized the Hamiltonian with fixed L2 norm. This is something fantastic, if you think of it. And actually, this was this observation inspired 1 century later. So the quantum is 1 century, for Blue, Benjamin, and Jerry to prove rigorously the stability of the KdV soliton. Okay? And also it can be viewed as the anticipation of famous Cazenave-Lyon's method to prove the arbitrary stability of ground state solution of Hamiltonian systems. Okay? Again, so this observation was really wonderful. This is okay. So go back to KdV. So KdV is a well-known equation for basically 3 reasons. First, it's one of the first examples of integrable equations. So that's following paper by Lax and Oscar Garnet and many others. Second universal asymptotic model for dispersive system in a correct regime, long wave, weakly dispersive. And third, it's a kind of case study for the modern method in dispersive PD, as when we see in the papers by Kenny, Poncevica, Bourgain, and many others. Okay? Nevertheless, the KDV has serious shortcomings. First, it's a one-dimensional model, so waves are usually two-dimensional. And mainly, it's a one-way model, so waves going in two ways in general. Okay? So you need to introduce system version of KDV, and that's what Vassilios did in the Vassilios system I showed you before. And after Vassilios, again, 1 century after, there was some isolated example of correct, well-posed Vassilios systems, like Brouwer, Bonda-Smith, Peregrine, Gou, and many others. And in the beginning, in 2022, 2004, and 5, Jerry, me and myself, and Jerry, Conan, and Lan derive in a systematic way, I will show you later, a class of Vassilios system. Okay, Hamming to, okay. And the same thing was done by Jerry, David, Lan, and me for internal waves. Okay. So, from that point of view, there are a lot of new difficulties with respect to the say, KDV or BBM equations. And also, there are plenty of Vassilios full dispersion system involving non-local operators, the non-locality being linked to the dispersion of the water wave, which, as you know, is non-local. So there is a very nice survey of a solution around Green-Langley type system. Okay, so what is the, first we have to define, as Vassilios did, some regime. And the regime we take here is the so-called Vassilios regime, so we consider weakly, nonlinear, and long wave effect at the same order, so we define two small parameters, which are essentially the same, so very often we take epsilon mu. And the correct way, and the only way to derive, to prove rigorously that those models are good models is to use the so-called Zakharov-Kreiskzulen formulation, the water wave problem. I mean, you writing the system in terms of non-local operator, which is directly to the main operator. So you put inside the small parameters and just to expand this operator. Okay? So you do that. And if you do that, you get this approximation of direct and non operators. If you plug it into the system, and you get this Vassilios system, which unfortunately is ill-posed because the coefficient in front of third-order term has the wrong sign. It should be negative to get the positive, to get the well-posed system. So what we did in this paper with Jerry and Min, by some transformation, so we arrived to a family of systems which depend on 4 parameters. So the system norm is known as the ABCD system. So there are some restrictions on the coefficient, which are here, A plus B plus C plus D equal 1/3 minus tau. Tau is a surface tension coefficient for capillary gravity waves. And for one, if you force the wave going to be one-dimensional going in one direction, say to the right, all reduce to the same KDV equation, which is here. So all of them give the same extension of the same KDV equation, which is here. Just a few comments on the system. So those systems are Hamiltonian if and only if B equal D, and K is Hamiltonian. So B and D are the coefficient of the BBN type, involving the T derivative. So here's the Hamiltonian. Okay. Now we are to prove rigorously, and that those models approximate rigorously the water wave system. So I will start by the last line. So the last line. So in the paper by Jerry Conan and Lan, so they had this error estimate in some subleft norm, but not precise, between solution given by the water wave system in this regime, okay, and the solution given by the Vassilios system. And the error is order epsilon square T, which is exactly the error what I derived a long time ago for the KDV equation. So now if you want to justify fully this approximation, you have to do 2 things. First, you have to be sure that the full system as solution on the correct time scale 1 over epsilon. Okay, and this is quite difficult. It was done by Andreas Medego and Lan, and mining Bing Zhang and Jiffy Zhang for capital waves. And second, you want to be sure that the Gaussian system has solution which live at least on time scale for the 1 over epsilon. Okay, and then you will make an error which is order epsilon. Okay, and I will focus a bit on the second, on the third point, which is not that easy. And first, since you have this family of systems, you have to make a choice. You cannot use all of them. So, how to choose a good ABCD system? So first, your system should be well posed. Okay. First. Second, you can choose ABCD for better mathematical or numerical properties, depending on your taste. Okay. And third, this is very popular among Gaussian graphers. You can, by Paddy approximation, so fit ABCD, choose ABCD to fit better with the whatever dispersion. So that's better you go with that. Okay. So if you have to have an insight on the properties of the system, you have to look at the linear part of the system, mainly on the zero eigenvalue of the dispersion matrix, which gave you essentially the phase velocity of the system, and you discover that first. It's quite easy to check that the Gaussian systems are linearly well posed if and if B, D are positive, A, C negative, or possibly A equals C. It's quite because you get a square, perfect square, but it's quite exceptional. And as I told you before, all the systems are equivalent in terms of consistency, but of course there are quite different properties mathematically depending on the order of lambda. So if lambda is order 3, you have another free system, the kind of two-dimensional KDV, if you want, system. If you are order -1, you have a kind of 2D BBM system, and in between, for when 2, you are close to some type of, it's a kind of Schrödinger type system, if you want, for short waves, the dispersion is very close to K to the square. And for instance, there is something which is purely mathematical. If you want to get the dispersive estimate, like equals 3 cars estimate, it's quite difficult. So there was a nice paper by Benjamin Benino from a student of David Dan, who tried to classify all the dispersive estimate you can get from this family. So it's kind of a mess, okay, but it can be done. Coming back to well-posedness, so it was checked, it was proven in the paper with Jamil Min that all the linearly well-posed systems are non-linearly well-posed, except 2 of them by elementary techniques, I mean energy techniques, except for 2 of them where you have to use some dispersive techniques. Okay. And actually the more dispersive Gaussian system corresponds to B equals 0, AC non-zero. That means that this system is a kind of, as I told you before, a kind of 2D extension of KDV, okay, third order. And it turns out that if you want to put local well-posedness, you cannot use energy. You have to use dispersive tools. So I just want to show you what you see. So you can just focus on the right part. Forget about the other stuff. So just locally well-posed in some space. But what is important is the index S of a Sobolev, so it's well-posed in the HS S, it's a 2-dimension, larger than 3 over 2, and on time scale of order 1 over square root epsilon. Okay? So I make a remark. First, this time scale is worse than the time scale you get for your pure 7-horn system. If you forget about the dispersive part, you get the 7-horn system. This is the hyperdeck system, which is symmetrizable. It's quite easy to prove that time scale is 1 over epsilon. So here you lose this time scale. Okay? Not a good one. And on the other hand, the exponent is better because you solve it locally in the HS larger than 3 over 2. But if you use the 7-horn, it's well posed in HS larger than 2. So dispersive effects allow you to gain something on the Cauchy problem. You can solve it in larger space. Okay? And this was obtained by using this modern dispersive tool. I don't want to. Okay. And there is another one which is quite a bit difficult, well, in the sense that we cannot solve it by elementary method. And this one is so showing the richness of this class of system is a special case of the so-called Euler Quadratic system, which is nothing but compressible Euler with capillary effect. Which go on the left, you have the compressible Euler, okay, this pressure law, and on the right, you have this capillary effect, which are the three, okay. And by a special choice of rho, d, and k, here you recover this the first Business system. This again. Well, now I'll go back to what it is important to get to fully justify the system is long-term existence. So just recall that the error with the fluidatory system as a result of Jerry and Conner and Lamb is order 1 square 2. And for the Business system, it's not so easy to prove this long-term existence. I mean, getting the hyperbolic time scale. Okay, and so I did many papers with my young Chinese colleague Li Chu, Chia Wang, and series of papers. Okay, essentially we cover all systems except one. I will show you this one. And so there was the result of Costin-Bourtia by a slightly different method, but with slightly weaker result. And in all the techniques we use with my young colleague, we use the non-cavitation condition, which is the physical one, saying that the surface cannot touch the bottom. Okay? Why? Because we use a kind of hyperbolic types techniques. So if you don't have a dispersive part, you symmetrize the Seminar system by a diagonal matrix, which is 1 plus zeta, 1 plus zeta. Okay? But if you do that for the Business system, of course, the dispersive part will put the mess in the. So you have to find a way to find a symmetrizer. And it's a kind of a mess because you have to do it for any system. This is why it took so we did it. I mean, we pick up some symmetrizer, okay, then we have to control the remainders, but it works. And we get exactly the correct time scale, which is 1 over 0. It's full, okay. And so why the fancy dispersive method doesn't give you the correct time scale? I showed you in the previous slide that the time scale we get was 1 over square root epsilon. It is because those techniques allow to solve the Cauchy problem with big solvable space. Okay. But they are quite, they do not take into account the algebra of the linear terms. Okay, when you can modify the system, you get the same result. Okay, but of course, all the questions linked to global existence or long-term existence are linked to the algebra of the system, and the algebra of the Seminar system. Okay? So this is why this kind of method never gave you the good time scale. And I told you before, so the method we use with Chinese young colleagues, so essentially are of hyperbolic nature. Okay, so and this is why you need this non-cavitation condition, which is of course physical because in reality the waves, the surface is not supposed to touch the bottom. And the musical, which is very difficult, the last case, it has some difficulty which occurs also when you want to solve the Cauchy problem for the water-wave system with surface tension. So it was done by Rousseau-Stetkov. It's more difficult than for purely gravity waves. For some technical reason, I don't want to detail that. Okay, so there is one which we call the nasty little duck, which is the only one for which we don't get the correct time scale. Actually, we get only the time scale 1 over epsilon to the minus 2/3. And the reason why is the only one, so one corresponding, which of course not physical, but corresponding to A equals C equal 1. So this is the only one for which the phase has some, some zeros. You have 1 minus epsilon square, so there is a set of zeros, and we give you some trouble. Okay, again, I don't want to be technical, but this is why. But this one, of course, is non-physical. It's just to complete the. And I don't know whether if you want epsilon is correct or not. So maybe not, but it's not very important. Okay, what about global representativeness? So the results are already a few. And essentially, it works only in Hamiltonian case, okay, so B equal D, and B equal D are to be positive. I mean, if B and D are 0, it doesn't work so far. And it works in basically two cases, BD positive and A and C negative, and A 0 and C negative. And it works in 1 or 2D, so in 1 it's another paper with me and Joey, and the extension to do 2D was just technical, was made by Hu. Essentially it tells you that if you take initial data small enough, okay, in terms of Hamiltonians, then you have global solutions for small data. You can see here, of course, the non-cavitation condition here, okay, 1 plus theta 0 positive, to ensure that coefficient of U square is positive in the Hamiltonian. To control the autonom of U, you have to impose this physical condition. So there are some nice results, recent results by Claudio Munoz in Chile. Maybe I don't want to. Well, they describe some asymptotic decay in subset of the light cone. These are very partial results of the asymptotics of those small solutions. Essentially, some subset of the light cone by virial techniques, Barbier techniques. Okay. So what's happened outside the light cone is unknown. What's happened in the case where A0 is unknown, and what's happened in the 2D case is unknown, and what happened in the non-Newton case is unknown. So lots of things are not known for the system. Finite blow up, another interesting issue. So as far as I know, there is no definite result of finite blow up for any of the ABCD system. This might be due to the violation of the physical condition of non-cavitation, but I don't know. So maybe, I mean, if you do numerics, this is starting from some silly initial data, you will see silly things. Okay, but of course it's not a proof. Okay. So there's a partial result by Galero being ensured that they gave condition on the solution to ensure finite blow up, but they do not connect this condition with initial data. So it's an if theorem. Okay. If I can produce initial data leading to this condition, then I blow up, but I don't know. So this might be empty. So now I have a conjecture about global representatives, and the conjecture is justified by the 1D, simple 1D case. So if you go back to 1D situation, like KDV type, so put epsilon in front of the sign in front of a non-unity and differential effect. So L, any self-adjoint operator, it could be the KDV1, Benjamin, whatever you want. So for this one, it's very easy to prove that there is there are two possibilities. Either we have global solution, or it goes up in time scale 1 over epsilon. How do you do that? You do change t, you let tau equal epsilon t. So you have the system in tau, there is no more epsilon. So for the system, there are two possibilities. Either you are globally well posed in tau, like with equals in t, or you blow up in time scale order 1 in tau, this gives you time scale order 1 epsilon in t. So there is no more possibilities. Cannot blow up. So this person either helps you a lot, I mean, go from Berkers, goes up 1 over epsilon, so infinitely defined, or it does not help you in terms of the time scale of the blow up. But there is no, okay. And, okay. But, so this is why you have this conjecture, but okay, I have no proof. For a system, you cannot use this trick. So if you cannot use this trick to eliminate epsilon in the system. So now there are two wonderful special systems, so in 5 minutes. So the one I call Tau Brouwer Copperschmidt system. So it corresponds, so I wrote it in 2D in the first system. So it corresponds to A equal plus minus 1, B, C, D, 0. So let's have a look on the 12. So this is the 1D case which interests me. So then alpha equal plus or minus 1. So when alpha equal plus 1, you have a so-called bad system because it's linearly imposed, and alpha equal minus 1 is a good system. So it turns out that when introduced by Brouwer and by as Waterway system, and by Kaup and Copperschmidt and Matev, Yavor as an integrable system. So it turns out that this system is integrable. Okay? In the sense you can. So integrability is not something which is well defined. Okay, so but okay. And so there are some aspects, recent aspects. It's a recent paper by Nabelek and Zaharoff, and recent prepared by Navelek in his group in Oregon. But there is no complete theory. Complete theory saying that I give you the shell data in some space, then I can solve globally the Cauchy problem using this kind of techniques. So it is completely open, interesting issue for the integrable point of view. Okay. So I'm trying to work with this with my friend Chris Ankland, but so far we don't have any stuff. So maybe Numerical will help a lot to present to see if there are this fundamental blow up. Okay, so but actually I must say that I forgot to quote the result of Jaime Angulo from São Paulo, who found, well, there was some sort of way for this, for the good one, and proved that it is stable, and also he showed the non-heritable conservation law, which of course was a kind of a hint of integrability, because here you have the Hamiltonian, okay, and Jaime discovered a conservation law controlling kind of second-order derivative, so it was a kind of suggest that this system could be integrable, and it is the case. I forgot to put the slide here. And the second I like a lot, well, physicists do not call it Emil-Schoenbeck, but I call it Emil-Schoenbeck in homage to Maria Schoenbeck and Charles Amick. So it's an old result. So it is a wonderful result by Maria Schoenbeck in '91. So this one is connected to the first to the impulse system. You know, I show you first when it's not the one derived by Vassilios, so the one you get from the first slide when you explain the question diagram. So if you do perform just a BBM transformation, a single transformation, you get that one. So it's a less transform. So you start from original one, which is impulse. You make one transformation, only one, and you get this one. So it's something that's closer to the first one. And it turns out that this is the only one, as far as I know, which can be viewed, and this is the observation of Maria Schoenbeck, as a perturbation of the Saint-Venant system. And you can use the structure of Saint-Venant to have some conservation law, I will show you next slide, allowing you to have global solution. It was a fantastic observation by Maria Schoenbeck. And this is actually the only case of among all systems for which you can prove global robustness for arbitrarily large initial data. Okay? Here are the results of Maria Schoenbeck. So essentially, he said if you take initial data in, well, so it was in C2, but this can be improved, arbitrarily large, then you had a global solution. So and Charles Amick had uniqueness, and he was improved some smoothness. And the idea I told you before is you have to derive a uniform bound, okay, using the entropy of the underlying Saint-Venant system. Okay? And after you use the factorization, you pass to the limit, and you get this result. And so this has been improved by recently by Molinet, Taluk, and Zaiter. So let me just give you the result I get. So the global robustness in HS is larger than 1 over 2, which is not a large space, but using the same techniques, but with some refinement at the technical level. And they were also able to prove global existence of weak solution. Okay, this lambda sigma 0 is a kind of Hurley's type space. Okay, so you take initial, it's rather weak large space, and again they use they use the idea of Maria Schoenbeck and Amick. I think that it's really a fantastic result. I mean, among all the family of Vassilios system. Now I will conclude by the bunch of open questions. So. Well, you know, there is definitely a number of questions. First, this Vassilios system will show you where they arrive with a flat bottom. Of course, in reality, the bottom is not flat. So we have a bathymetry. So you can do bathymetry and try to divide model in this regime. So this has been done for many people. Probably I forgot a lot of names, but well, it depends on the bathymetry. If bathymetry is slow, it's what to be straightforward. If it is not, it's not that straightforward. Okay. Well, there are a lot of results, of course, about, I didn't say a word about suitable solutions that are very nice work, like independent coding mean here. So, you know, but there is no, as far as I know, a complete classification. You know, give me ABCD, so I cannot tell you immediately, so there are certain ways, there are several or not, but there are a bunch of new interesting results. So recently I have a long-time result with my from the postdoc student on long-term existence of the background of a line soliton, when there is such a line soliton. Where there are lots of people doing control theory of this kind of system, for the linear and non-linear one. There are people doing non-trivial geometry, so you go back to Stanasis. Some people using a forecast method to prove resistance on, say, such system on the half line. So put names here, but not sure complete. And so far, last observation. So we didn't find a relevant system for which the existence type is larger than the public one, except the Schoenbeck-Boussinet system, but you have global representativeness. And well, there are some. Well, so maybe I will skip the. And of course you can do the same. So you have plenty of one-way model for waves, interval waves. So Benjamin Hollow, the long wave, and of course you have the system version of that. So you have the Boussinet version, the older system with a lot of problems. Okay. Okay, so it's still a lot of work to be done. So including integrability for the Kirk-Bauer potential, which is nice. I mean, it's a very nice question on integrability. Thank you very much for your attention.
If I make a remark,
Sure.
because you mentioned this Zakharov, Sullem, Craig,
Yes.
Neumann.
Yeah.
You see, as you know, this is in the form of a series, I would say an ugly series, using the global relation, which is part of my method. We wrote a paper with Markowitz and Slimani, where we saw that these actually are the first term of the Neumann expansion of a very beautiful integral equation, and more importantly, we extended this to 2 dimensions, and then very, very simply we get KP, we get Menirasti system, which, as you know better than me, is the 2+1 analog of Boussinet. So this is, I think, an important development. But there's, in my opinion, maybe a more serious remark, and this is, of course, you gave a very beautiful review of what has happened with Boussinet, but there is some point that should be emphasized, and this is Boussinet is a limited system in the sense of geometry. If you go through this, we extended later this approach to a complicated geometry, and then although this approach where this global relation works for any geometry, you get Boussinet only in a very limited case that the geometry is very simple. So if you really want to examine problems like generation of tsunamis, have a moving bottom, etc., you have to go beyond this and go back to the correct formulation of the Dirichlet-Neumann map, which is provided through this non-local equation.
Other questions?
Good thing we're not going to be on the job anytime soon. Just a remark.
Yeah, sure.
The calc system, which you have, which is linearly opposed, actually Ambrose and I showed it was non-linear.
Yeah, okay, I forgot. Okay, sorry, yes, I forgot to say that. But the next paper, I want to compress my slide. There's a nice paper by Ambrose, Jerry, and everyone, showing that the linearly opposed top system is non-linearly opposed in a very strong sense. Right? Yeah. And nevertheless, we have global distribution in some global spaces. So it's good. You have to do us. You have to speak on it. It's a nice paper. Yes, it's for the imposed curve version.
Right.
For the imposed
So the ABCD systems that are linearly opposed, all but one of them, or these two, we showed was non-linearly opposed.
Okay. I don't know this. Which,
I can find it.
No, yeah, sure. That's sorry for the process.
Any other questions or comments? If not, let us thank Professor Shaw. outside for the conference photos.
better here, okay? That's time 3 pi over 4 at the top, and you definitely see that there are oscillation. Below is time 3 times an approximation to pi, 3.14 over 5, and you see fractalization. So it's really, really important that you're computing at that specific time. But there are this, and in fact, these oscillations are the origin of the fractalization. When you try to approach an irrational with rational numbers, these oscillations, the denominator increases. There are oscillations all over the place due to Gibbs, and this is what creates this fractal structure. But I won't be there. There is this is the proof for all this equation, for all these linear dispersive problems. You can actually, at these special times, you can write the solution in this form. And this is a finite sum. Okay, so you write the solution, u at time, which is 2 pi over p over q, so a rational multiple of the period, as a finite sum, which has u0 at certain points, so whatever the initial condition is, times some coefficients, which are given by these Gauss sums. And to prove this is very simple, actually. I have a slide by it. I won't go into it, but it's just elementary number theory, really. And again, this is, so the picture at the top, which has, it's a rational multiple of time with a denominator equal to 978, just to show you how well this works. Below is the solution obtained by truncating the Fourier series, and above the one obtained by these finite sums. Okay, but this finite sums is only valid at these special values of the time. Okay, so that's what the Talbot effect is, and that's all well and understood and for the periodic problem. Peter had also done some numerical experiments for problems with non-polynomial dispersion relation, water wave stuff. Okay, and he had found some interesting things, and heuristically, based on his numerics, he conjectured that this quantization fractalization, if you linearize the water wave models that have these linear dispersions, this phenomenon would only arise when asymptotically the dispersion relation goes like power of k of mod k larger than 2, larger than or equal to 2. So for KdV, which is k3, okay. For linear Schrödinger, k square, okay. Should be okay for BO as well, Benjamin-Ono, because the dispersion relation is k mod k, so it's like mod k square asymptotically. And, but not the others, not BBM, Boussinesq, yes, but not BBM, for example. And indeed, there is some recent work on what happens, what's the evolution of a discontinuous initial condition under BBM by these people. So it's very different. Doesn't have this Talbot effect. So when we work together to try and understand what happens for linearized Benjamin-Ono, which is this equation, is non-local. It is described by the periodic Hilbert transform, which is here. That's just to show you the equation in Fourier space. As I said, this is the dispersion relation. He had produced some pictures, and these are the pictures that these are not exactly the one that he had produced. I produced these, but these were the kind of things he had found already. This is the solution starting from that step function, the simple step, at time that is generic or at time that is non-generic. And you should imagine these cusps infinite. It's certainly very different, qualitatively different. It has also, these are other different multiples. There are cusps. There are also these jumps in some places. So there seems to be some form of Talbot effect, but certainly different from what we saw for the local linear equations. And so we wanted to explain this. And if you write down the Fourier solution of the problem with a step function initial condition, you come up with something like this, and you can start manipulating it. And of course, you may know Peter Albert comes from a family where special functions were bread and butter in the morning. And so he knew, as soon as we wrote it as a final final sum like this, that these things that we could represent these as some special function. He went, looked at it, and indeed they are trigonometric hypergeometric functions. So this is just hypergeometric functions. The real part of some hypergeometric functions restricted to the circle. Anyway, they exist in the list and catalog of special functions online, the digital library, and a lot of their properties are listed there. You can go and spend your time doing it. In particular, you can write down what the distributional derivatives of these special functions look like, and they are finite sums of delta functions and cotangent terms. So that looks promising. Well, it didn't actually ring a bell right away, but it should look promising because delta functions mean that you pick up values of the initial conditions, whereas the cotangent was in the definition of the Hilbert transform. So what do we do now? And what we did, because this representation is a finite sum, but it doesn't tell me explicitly where the initial condition is. So it wasn't useful for reading off what type of representation in terms of the initial condition, where are the finite values of the initial condition here? We wanted to find that. And it's not very difficult, but if you worked a bit, you find that you can represent the fundamental solution of this. So the solution that corresponds to starting with a delta function. It's a distributional solution, but you can formally make sense of it, and you can write it in terms of the derivative of these special functions, and this derivative of special functions have deltas and cotangent terms in them. And so using that, yes, that's what I just said, using these two facts, that you know exactly the shape of these derivatives and that the periodic Hilbert transform is defined as an integral with cotangent, and that if you have the fundamental solution, you can get any other solution by just, yes, I can't think of the word, then we proved that at rational time, the solution to the periodic initial value for Benjamin Ono, starting from, well, the step, because this is only done for one step, but this is clearly generic of any discontinuity, is a finite linear combination of translates of the initial condition, just like before, but also translate of the periodic Hilbert transform of the initial condition. That was quite neat, and we were very happy with that. So happy that we thought, what about other non-local dispersive problems? And so we also did the intermediate long wave equation, which is similar. In fact, it interpolates in a sense between Benjamin Ono and KdV in the two limits as this parameter delta, which is the depth goes to 0 or infinity. It has a dispersion that again goes to something like k squared in the leading term at infinity. So we looked at this, and what we could prove is that it doesn't exactly have this Talbot effect, but approximately is what we call a weak effect. So the solution of this problem you can write as the solution of the BO problem, all linearized, I should stress, but translated, plus some function that is C infinity, and that in fact is very small. It is so small that you cannot see it in the numerics. You see, this is the solution to the same for the same initial condition of BO and intermediate long wave for, I don't know, delta is 1 here, and you just see the shift. You don't see any difference. The difference is very small. So you inherit. We actually did also the Smith equation. That's for Jerry. It's a bit more complicated because you cannot write the operator in closed form, but you can say something, quite a lot. Okay, so I don't know what time it is, but I'm sure that I'm close to my time. Yes, let me just show you some nonlinear pictures. For the nonlinear problem, we don't have any proof, but this is the full nonlinear Benjamin Ono equation starting from a box. And again, you see this effect. There is a proof by Erdogan and Tsirakis for nonlinear Schrödinger and KdV now, and it's based on splitting the solution in the linear part plus something and proving that the something is continuous, so it won't affect the discontinuities if they are there. and that's based on Bourgain estimates and so on. That's all periodic problem. So this is what happens for the nonlinear Schrödinger or for the full nonlinear KdV. So you definitely see this effect. And I should comment on the numerics for this, because it's absolutely non-trivial to do the time stepping for full KdV with the rough initial condition. Okay, so this was done by a scheme of somebody who was a colleague of mine for 3 years, and now is in Paris, Katerina Schratz, who has a very ingenious scheme, numerical scheme based on resonances for computing these things. She actually also did affine initial conditions. And nothing about integrability, I didn't say, but this has nothing to do with integrability. The same thing happens also for quartic KdV, which is not integrable. So that's my picture slide over. I'll just leave you with a picture that I really treasure. It was taken at Vassilios' retirement party, and some flowers from my garden for him. Thank you.
Any question?
Quick question. So I didn't understand the final statement about the nonlinear problem. So this phenomenon persists or not?
It does.
But it doesn't watch it, because the pictures don't reveal this, unless these oscillations are artifacts.
In the sense that the solution is the solution of the linear part, which does have these discontinuities, plus a continuous function, which alters it, but does not change the discontinuity. So it has the discontinuities. If there are in the initial condition, discontinuities will persist in the solution, but it's not an exact reproduction of the initial condition.
But this element, in that sense, it doesn't persist.
It's a weak effect.
Okay.
Yes.
That's very good. One second, one more statement. What about non-periodic? Any of these persist?
So, in a weak sense, a lot of it, but not for even for linear KdV. It has to be very special. So, say linear Schrödinger with Dirichlet or Robin boundary condition. Dirichlet is like periodic for linear Schrödinger. You just double the period and it's fine. Robin is not necessarily like periodic, but there is this kind of weak effect. So the discontinuities are reproduced, but not the exact form of the initial condition.
Just like the nonlinear.
Yes.
Okay.
So we call it weak revival. But for KdV, for linear KdV, it breaks much faster. It has to have very special symmetries in order to survive.
So this effect basically is sort of some pathology of things of the periodic problem.
It's absolutely, so when you see it, it's an echo of periodicity. And without that echo, it just doesn't survive.
I wonder if this effect that you showed of recurrence has any relation to the breather solitons.
No, because this is quite different. You know, it's a pointwise effect at certain special times. Generically, the solution is not at all like that.
Okay, thank you.
Thank you.
Next picture is Angel Duran from the University of Valladolid.
Thank you.
And his talk is titled The Last Valse of Boussinesq's System for Internal Waves.
Thank you so much. Thank you for the kind invitation. Let me first give a short explanation about the title. Yeah. It's okay. The Last Waltz is the name of a film, let's say actually a documentary, on the last concert of a relatively famous American musical group in the 60s or 70s. They played with Bob Dylan, with a Nobel Prize, so they should be important. Of course, I took the name with a completely different meaning. My talk is about our last publications jointly with Lita Saridaki, his last student, who recently defended her thesis with success. Last thesis with Vassilios as advisor, hence the last words. Okay. I organized the talk like this. Our work was a project on some differential systems for the propagation of long internal waves in some Boussinesque region called Boussines systems. They were derived by Bona, Lanz, and Stott, among other asymptotic models. So I will take some time to summarize their derivation and the main mathematical properties. Some of these properties were analyzed in our work, but our main contributions concern two points: the numerical approximation of these equations and the existence and dynamics of solitary wave solutions. In the first case, we derived some error estimates for the spectral Fourier-Galerkin semi-discretization of the periodic problem. And as for the solitary wave solutions, we obtained some existence results from the application of several standard theories and studied by computational means aspects of their dynamics. So I hope to be able to give a good description of the results. Okay, the Boussines systems were derived as a model for the propagation of internal waves along the interface of a two-layer system of fluids sketched here in this figure. The layers have depths D1 and D2, and densities rho 1 and rho 2. The upper layer is restricted by a rigid lead assumption, and the bottom is horizontal, impermeable, and flat. And no surface tension is considered. The one-dimensional version of the Boussines systems has this form here. Zeta denotes the deviation of the interface from rest position. U is a velocity variable appearing in the system in a non-local way through this new variable V. And gamma and delta denote respectively density and depth radius. Okay, as you can see, the system depends on 4 parameters from A to D, sorry. But since these parameters can be described in terms of 3 modeling parameters and they satisfy this relation, it is actually a 3-parameter family of equations. Bona, Lanz, and Stott proved that the Euler equations for internal waves are consistent to some order with these equations under some Boussinesque region that Jean-Claude mentioned before. This means that we have similar depths and comparable small dispersive and nonlinear effects for each fluid. Okay, our work was initiated by reviewing some results on the well-posedness of the corresponding initial value problems and using the corresponding results for surface waves obtained by Bona, Chen, and so. First, the standard theory using Fourier transform and applied to the linearized system implies that the Boussinesq system is linearly well posed in this admissible set of parameters, of values of the parameters, and on suitable Sobolev spaces, and they are determined by the order of this symbol, which appears in the Fourier representation of this linearized system. Concerning the local well-posedness of the full nonlinear systems, meaning existence, uniqueness, and regularity local in time of solutions, we applied as well the corresponding results by Bona, Chen, and Sot for the case of surface waves, and we obtained 7 cases of local well-posed systems in the internal wave case. Here I indicate these 7 cases here in the next slide, and I also put the admissible set in the corresponding case of values of the parameters and the Sobolev space associated to local well-posedness, as well as the theorem from the paper by Bona, Chen, and so that we applied, corresponding theorem. So we obtained seven local well-posedness results. More regularity results for some of these systems can be seen in the paper by Kundian. Okay, additional properties of the Boussinesq systems concern the preservation of some invariants by the evolution, including the Hamiltonian formulation given by this quantity h that holds in the same case as in surface waves when b equals d. Other results for surface waves concerning recent results concerning long time existence and asymptotic behavior of solutions can also be applied to study such issues in the internal wave case. Okay, let me make a first break. So this picture was taken by Tina in 2007 in my city in Valladolid during her second visit, I think, with Vasily and Professor Dimitrios Mitsotakis. The picture for me is interesting not only because of the people in there, of course. It was cold, by the way, but also because of the buildings around. Close to us, there's the main administrative building in the university in Valladolid. It was a former Palace of Justice. I mean, Chancillería is called in Spanish. Including this building included jails and torture chambers as well. Okay. We still put some students inside from time to time these days. Oh, I'm sorry, not students. I made a mistake. Teachers, I meant. Okay. On the other side of the street, where Tina was to take the picture, there's a small church, small but important, because there the Catholic kings were married. So we are talking about Middle Ages and beginning of Renaissance. Okay, let's come back, fortunately, to Boussinesq systems. Our next step in the study was about the numerical approximations. So to this end, we considered the periodic initial value problem for the systems, written now in this this form and in this spatial interval for simplicity. And we assume that the problem has a unique solution which is smooth enough for our purposes. This regularity is determined by this parameter mu. Which are our purposes? Our purposes are to obtain error estimates for the spectral Fourier-Galerkin approximations to this problem. So we define the corresponding semi-discretization, the semi-discrete solution, as a pair of functions, of T on the corresponding space of trigonometric polynomials, and satisfying the Galerkin conditions with respect to the L2 inner product, as usual. Okay. So we obtain some error estimates for each of the 7 cases of nonlinear well-posed systems. I have gathered the results into 3 groups, depending on the norm of the error considered, L2 times L2 or L2 times H1, and also depending on the decay, determined by this parameter of regularity of the exact solution. In all the cases, in the smooth case, for smooth data, all the results imply a spectral convergence. Okay, these error estimates can be experimentally checked by discretizing the equations with full discretization in time. So to this end, we consider the semi-discrete differential system derived from the spectral Fourier-Galerkin discretization. We put the system in the Fourier space for the discrete Fourier coefficients of the approximation, and we integrate this differential system in time with a 4th order Runge-Kutta composition method from this family, 3 stages and these 3 parameters. This family comes from the composition of the implicit midpoint rule. Okay, so we check the full discretization for accuracy, stability, and performance by some numerical experiments. And by way of illustration, I can show you some of these experiments. For example, in this internal wave case, we can obtain exact formulas for the solitary wave solutions using the same arguments as Min did for the surface wave case, specific speeds as well. So we obtain one of these exact solutions. We compared with the numerical solution, and we constructed this. For example, these 2 tables of errors for 2 different values of the number of discretization points and different time steps. Here we show the L2 norm of the 2 components of the numerical solution and the temporal convergence rate, which is 4 because we obtain a spectral convergence in the space. Okay, for example, second example of numerical experiments, we can measure the behavior of the full discretization with respect to some parameters of the wave. So in these pictures, we show the time evolution of the error in speed on the left and error in amplitude on the right with this fully discrete scheme. And in both cases, we obtain some error which is bounded in time and that is small. So these and other experiments gave us some confidence on the accuracy of the full discretization and enabled the code as a good code for our next step in the research, which was the study of the existence and dynamics of solitary wave solutions. Okay, but before that, let me show you a second picture. This was taken in 2009 during my second visit to Athens. This picture was, of course, taken by Tina as well. We went on a trip to Cape Sonion. Tina took many, many photographs, and she was very kind, but after that she sent me a compact disc full of them. So among all these pictures, I took this one, which I think I like the most. Here you can see Vassilios and I as good students of waves, honoring the god Poseidon in his time. Okay, this is a nice picture for me. Well, let's come back. Our next step in our project was concerned the solitary wave solutions of these business systems. These solutions are traveling waves with permanent form and a constant speed, so the profiles must satisfy this differential system. We focused on the classical solitary waves, for which the profiles must decay to zero at infinity. Therefore, this first system is simplified to this one. But we also considered solitary waves which are not classical, in the sense that the profiles oscillate at infinity instead of decaying. They are called generalized solitary waves. Well, so we first applied several standard theories of existence in order to obtain some results, and the main ones were derived from the application of the normal form theory, which is a local theory based on the linearization of the system for the solitary wave profiles at the origin, considered or written as a first order system. So we obtained these two groups of results. One for these values of the parameters for these ranges. They gave classical solitary waves with monotone decay. And for the second group of values of the parameters, we obtained the existence of generalized solitary waves. These results are local in the sense that the theory ensures the existence of the waves for speeds greater than but close to this limiting value as speed of sound, and depending on the depth and density ratios of the problem. In addition, the normal form theory also predicted two other groups of traveling wave solutions. The first one is given by periodic traveling waves close to the region of generation of these classical solitary waves. But we also obtain a second group of classical solitary waves with no monotone decay for speeds limited by this speed of sound. I can illustrate some of these families. For example, this picture corresponds to a generalized solitary wave. You can see the oscillations at infinity here in the profiles and also in the corresponding phase portrait. The second one is an example of classical solitary wave with monotone decay. And the third one is an example of classical solitary wave but with no monotone decay. So in general, exact formulas for these waves cannot be obtained, and therefore we have to construct some numerical procedure in order to obtain approximate profiles. So the one we took was based on two points: the discretization of the system for the profiles by using a Fourier collocation method with periodic boundary conditions and on a long enough interval, and then the iterative resolution of the resulting system in Fourier space, which leads to an algebraic system that can be solved iteratively. The remaining theories contribute to these results, to this study, with some existence results, but for the case, only for the case of classical solitary waves with monotone decay. For example, Toland's theory and concentration compactness theory can be applied in the Hamiltonian case, and the first one gives a sort of a speed amplitude relation, as in the case of surface waves. We can also apply the positive operator theory. In this case, the corresponding result does not require the Hamiltonian structure, but the hypothesis of decay, of monotone decay of the waves is necessary. Okay, so the last step in our study was to develop some computational work about the dynamics of all these solitary waves. Of course, to this end, we considered the initial value problem with periodic boundary conditions, and for different initial conditions, we discretized the problem with the full discretization, full approximation that I mentioned before. And we monitor the corresponding numerical results, the behavior of the numerical solution. In the case of the classical solitary waves with monotone decay, the experiments were made from initial data consisting of small and large perturbations of the approximate solitary wave profiles, superpositions of these solitary wave profiles in order to study the solitary wave interaction, and also Gaussian pulses as initial conditions in order to study the resolution property, the resolution of more general initial data as a train of solitary waves. So let me summarize the conclusions. For small perturbations, I'm sorry, this was not first. For small perturbations, the experiment suggests that the solitary wave solutions are asymptotically stable in the sense that the numerical solution evolves into a modified solitary wave with an asymptotic, say asymptotic speed, and along with two types of dispersive tails trailing this wave, the main wave, but traveling in opposite directions. If we increase the size of the perturbation, some other small nonlinear structures may be generated of different nature. We may obtain classical solitary waves with monotone or no monotone decay, or other nonlinear waveforms, for example, of wavelength type. As for the collisions are, as expected, inelastic. So after the interactions, two classical solitary waves of the same time emerge with different speed and amplitude compared to the original before the interaction, and the corresponding generation of dispersion after this phenomenon, and in some cases small nonlinear structures. In the case of the resolution property, let me illustrate this with these experiments with two pictures. These two pictures here from the Gaussian profile of this form with these values of the parameters. We run the code after 800 units of time, and the corresponding numerical solution evolved into a train of classical solitary waves with monotone decay and traveling to the right, and leaving a small structure here behind, which seems to be dispersive. Okay, this is a typical experiment that we made in the case of Gaussian perturbations. What happened with generalized solitary waves? Here, the experiments with small perturbations suggest a sort of stability similar to the case of classical solitary waves. But to obtain these conclusions, we need to reduce somehow the size of the initial perturbations, and we have to run the experiment longer compared to the case of the classical solitary wave. The second problem is the generation of dispersive tails from these small perturbations, because they are hidden in the ripples of the wave. So they may be small and sometimes are hard to detect. If we increase the size of the perturbation, we obtain similar conclusions to those of the classical solitary waves, in the sense of the formation of small nonlinear structures overimposed on the ripples of the wave. The waves oscillate at infinity. And another phenomenon that we observed was the formation of larger ripples and dispersive tails just in front of the emerging generalized solitary waves, which surely affects its stability. The main effect observed for the case of collisions, overtaking collisions and head-on collisions, was the formation of course, two emerging waves after the interactions, two emerging generalized solitary waves. But in general, the ripples after the interactions were larger than those of the original before the interaction. And contrary to that, the dispersion seemed to be weaker, I don't know, smaller, compared to similar experiments that we made in the case of classical solitary waves. Now, is there a resolution property for these kind of waves? Well, yeah, there is a resolution property, but more. Let me illustrate this phenomenon. So from this Gaussian profile here in rows, the corresponding numerical solution evolved up to 800 units of times, had several structures. On the right, we have a train of generalized solitary waves. They generate ripples. We have ripples and dispersive tails between two consecutive profiles. Some dispersion is also generated behind the train, behind this train. And on the left, we observe another structure, and this corresponds to a train of solitary waves, but now classical solitary waves with no monotone decay. So the numerical solution evolves into these three structures. Then, motivated by this, by the generation of this family, we still made computations about the dynamics of this second family of classical solitary waves, and the conclusions seem to be similar to those obtained for the classical solitary waves with monotone decay, but with some differences concerning the type of dispersive tails observed, and also the nonlinear waveforms that may be generated in this case. Okay, let me show you a final picture to end this talk. This was taken recently in 2019 in Dougalis, the north of Spain, in a conference that was organized by Vassili, by Ted Casaonis, by my colleague Begoña Cano in Valladolid, and by me. And I'm happy to see here many people in the picture. Okay, so this was the last picture, the last conference, and hence the last one. Thank you so much.
Question?
So you didn't see evidence for finite time growth in the simulations?
Nothing.
Is there any physical relevance for the differential
You mean classical?
Have they observed any of those kind of short-term waves apart from the classical ones?
Yeah, I remember some papers about the generalized solitary waves. I don't remember now. And in the case of classical waves with no monochrome behavior, I don't know any paper.
I just have suddenly have a curious thing. So the negative wave always look like that, you know, from your tails, and the largest one is in front, right? So it's like that. So what happens if I have two of them, the larger one before? Is that going to do something like solid wave taking over?
Who knows?
But see, the big one is in front. Then I put the small one. See what happens.
Yeah, well, you could do that.
Yeah, see what
That would be an
happens.
interesting experiment.
Yeah, see what happens. So like, you know, the solid wave, which in KDB, it's the singe functions. So one catches the other and retain the shape. Right now, if you have two depression and one catches the other, what happens?
He hasn't done that experiment yet.
Yeah, we didn't observe it.
What's next week?
Yeah,
We may try.
Yeah, I may try. I don't know. Just suddenly feel like just that somehow that structure seems to be always shows up. It's almost like solid wave always shows up, and that structure always shows up. So it might maintain shape. Don't know.
Any other question? Okay, thank you. I would like to thank you all the speakers of this session. Chrome, δεν είναι. Τα παιδιά που στείλουν το βίντεο,
Προφανώς εδώ αυτό έχει θέμα με το δικό, δεν ξέρω γιατί. Το έχει ξανακάνει δηλαδή.
Κάτι παίζει με τα πρωτόκολλα ασφαλείας. Κάτι με το. Τα Mac το έχουν αυτό. Είχα και εγώ Mac και μου βγάζει κάτι άλλους τέτοιους προβληματάκια.
Δεν έχω VPN.
Το VPN δεν έχει σχέση. Το VPN είναι virtual private network. Είναι στην περίπτωση θέλετε να συνδεθείτε σε έναν υπολογιστή σε ασφαλές δίκτυο.
Στο γραφείο, στο Πανεπιστήμιο του λέω κάτι παραπάνω από αυτό που είναι το κόμμα της
υπάρξει. Θέλει και ομιλητές όμως να. Δηλαδή, εξαιρετικά να πάνε και μιλάνε.
Ναι,
για
ναι,
μια
έχει
συζήτηση.
από όλες τις παραλλαγές, ακριβώς.
Το οποίο εντάξει, αυτό τώρα.
Και το ένα και το άλλο.
Εν τω μεταξύ, είμαστε live streaming, μας ακούνε, να ξέρετε. Οπότε ό,τι κατηγορήσουμε. Ναι, σαφώς.
Κάνουμε και καταγραφή ή...
Ναι.
Ναι, recording.
Είναι στο YouTube.
Α, μάλιστα.
Πείτε μου.
Λοιπόν, στο Quiet Med θα πάμε εδώ. Scarce Leadership Noise. Αυτό.
Ένα PowerPoint επιτέλους.
Είμαστε στο τελευταίο session.
Στο
S4.
Ένα λεπτό, πείτε μου τι ώρα μιλάτε.
Τέλος, η τελευταία ομιλία είναι.
Εδώ αυτό.
Ναι, ναι, αυτό.
Άρα είστε στο 4. Έχετε δίκιο.
Τέλεια. Και δεν κάνουμε διακοπή στο live streaming στα διαλύματα.
Το έχω βάλει να παίζει γιατί δεν θέλω να το διακόψω για να μην χάσω το link, μην έχουμε κανένα. Μετά το μοντάρω. Έτσι κι αλλιώς. Γιατί δεν είμαι σίγουρος ότι.
Δηλαδή γίνει καμία.
Δηλαδή χάσουμε και μια στιγμή δηλαδή κάποιος πει δεν θα μπορούσα να το δω γιατί θα διακόψει.
the organizers. It is a real honor for me to be here. I would like to say a few things about Vassilios, perhaps at the end of the talk. But now at the beginning, I would really like to justify a bit the topic of the talk, because I tried to find parts of my research to present today that are perhaps more closely affiliated to the work and the influence that Vassilios had. So this, what I'm going to talk about today is the first half of a PhD thesis of Dimitra Plaka from the Technical University of Athens, under the supervision of myself and Kostas Christafinos. Both Kostas and myself used to be undergraduates at the University of Athens, and we were initiated in numerical analysis by Vassilios in his lecture. And also you may think that this is the outlier here, Zhao Nandong, who is in INRIA. He's a permanent researcher in INRIA Paris now, but actually not. So when this work was taking place, Zhao Nan was a postdoc in this very building, in this very institution. So it's also something as close to work of Greek numerical analysis. I have to say that this research was supported by the Hellenic Foundation of Research and Innovation through two separate grants, one for the PhD students of Dimitra and one for Kostas and myself. Okay, so the problem, I appreciate that there are few world experts in the audience on this problem, but for the benefit of everybody, I will try and give you my take on this. So the Allen-Kahn equation is an equation that is a typical, prototypical example of phase separation, phase field equations. So equations whose solution tries to represent two different phases. Okay, so it has stable equilibria in the two different phases. And as a numerical analyst, what we like, here's my epsilon, Chrysula, we like to see challenges, and this equation is certainly challenging in terms of numerical analysis, because as we will see, it has singular perturbation. So the Allen-Kahn equation is interesting because it describes a limit problem as epsilon goes to 0, the mean temperature flow. But unfortunately, the interface length has to be small enough in order to describe the correct dynamics. And if we want to solve this problem numerically, this is highly challenging, because solutions of phase field equations could look like this. Okay? So things go to +1 and -1, or 0 and 1, depends how you normalize. Okay? And you have steep layers from one phase to the next, and then the size of the layer is order epsilon. And I have 1 over epsilon squared there. So in order to approximate these solutions, I need to work very hard, at least at the interfaces. And typically, because I need to resolve all the scales, this is a very difficult problem if I'm just using some sort of numerical method that has uniform resolution over the whole of the domain. So this is already creating a lot of trouble. Now, one may start observing the fact that solutions to these equations, at least relevant solutions between, say, -1 and 1, or things like that, spend most of their area being at 1 or at -1, except from those very steep interfaces that one has to resolve. So why not thinking that maybe one could apply some modern numerical techniques whereby you have the opportunity to design numerical methods that admit very general shapes, very general computational elements, cells, you call them as you like, okay? And this is the second part of the talk, so we actually try to do that. And really, the hope of this project is to arrive into something like this. So let me try and make this a bit larger. So this is just heat equation with some forcing. So this is not the Allen-Kahn problem. But what happens is that the heat equation, the solution stops around 1. And what you would really like, using standard numerical methods on triangulations or quadrilaterals, even if they are adaptive, like they are here, that they're able to automatically adapt the mesh. You really would really like to be able to have very general element shapes, because this is just one. It's very easy to approximate one with very few degrees of freedom, numerical degrees of freedom. So ideally, this is something where we want to arrive. Okay? So this is the dream, this is the hope. Let me show you some of, this is the same thing. Let me show you some of the steps. Now, just solving these equations numerically is difficult. What I would really like is not just to discuss about numerical methods, their stability, etc., but what I would really like is to devise rigorous, computable error control. So what I really want is to be able to tell my method, here you should put more resolution near the interface, or here doesn't matter, you don't need to put more resolution. And I want this to happen automatically. That is the whole point. But Alan Kahn is not on my side, because it has two fundamental difficulties in terms of, at the PDE level, you don't need to do numerical methods. It's not monotone, and it's singularly perturbed. Okay, so this minus here is not doesn't make us very happy, but this is what gives all this nice structure and becomes a relevant problem. And this interface length, you want it to be as small as possible, but that creates difficulties in approximation. Okay, so just to indicate why this is a difficult setting, if this is not apparent, if we just use standard Grow-Wall estimate here, what you will find is that you have to divide by the interface length. So stability is there at the PDE level, okay, but it is exponentially bad with respect to the interface length. Okay. So the PDE stability is what I'm after when I'm trying to prove a posteriori bounds for numerical methods, for Galerkin methods. So this is classical, and people in PDE theory, some people are in the room, like Nikos, have thought about this, I hope, long and hard. And a classical way out that appeared in the early 90s was a crucial observation for this system, and similar observation exists for other phase field equations. So if we look at the Rayleigh quotient, so of the linearized operator, this is the spatial operator, and we just divide by the L2 norm. So this is the first eigenvalue. If we look at that, and we call this lambda AC Alan Kahn, for spatial regimes who have developed interfaces, etc., this lambda, despite the fact that I have a singular perturbation here, was shown that for certain initial conditions, etc., spatial regimes, that is independent of epsilon. So and this is these papers, and also there's work by Nikos and Fusco. So this was very interesting, because this is a complexity help. Okay, things are looking very bad, but actually for this for this PDE, they are not so bad. So this was taken up very early by the finite element community, by the computational PDE community, and Xiaobing Feng and Andreas Prohl in 2003, in a seminal paper, they assumed that this spectral estimate is valid, okay? And using that, instead of an exponential, they proved error bounds. So this is some sort of truncation error, you can think about it like this, these are error bounds that were polynomial with respect to epsilon. Okay, K may be bad, but it's not exponential. So this is the whole point. So there is polynomial dependence. This is classical nowadays. And of course, this is a very interesting idea. Look at the linearized operator and see how bad the eigenvalue is, because this will be your constant in your ground wall, essentially. That's the whole point. So this spectral estimate has been quite popular as an assumption For instance, Bartels, Müller, and Ortner in 2011, while proving a posteriori estimates for this problem, they postulated that this eigenvalue, okay, I mean, this was known, I guess, that this eigenvalue, when you have topological changes, when you have one, for instance, one phase splitting into two pieces, etc., this eigenvalue indeed will go to infinity. But what they discovered numerically, this is not a theorem, is that this eigenvalue is integrable in time. So it's L1. It goes to infinity in an L1 sense. So, and they assumed, I don't know how relevant this is, but they assumed that one reasonable assumption to have about this eigenvalue is that is bounded by a constant plus a logarithm of epsilon to the minus the number of topological changes, because this is how many integrals of this kind you have to take in time. Okay, so this is a reasonable assumption. So now let's think. We have numerical methods. I haven't shown you one yet. And people have been trying to prove computable bounds, a posteriori bounds for such numerical methods. And there I'm grateful to Theodoros Katsaounis, who in his talk explained a lot about a posteriori bounds. Okay, so in a posteriori analysis, whereby you use the PDE stability to prove those bounds, I'll show you how it looks later in the talk. The first paper in a posteriori analysis, also a seminal paper, was by Riccardo Noceto, Kessler, and Smith, where they assumed the spectral estimate, which may not necessarily be true in the settings that we have, and they did a conditional, as we say, a posteriori error analysis. So a computable bound holds under a condition of smallness somehow. So Feng and Wu did a similar, a corresponding result using a nonlinear ground wall. But this is not very practical because this assumes that you are linearizing about the exact solution, and that's not what you have in practice when you compute. So you want to know what happens with the eigenvalue around the approximate solution. So I'm going to call UH my approximate solution. And indeed, after these works, perhaps the most comprehensive paper is this, and quite seminal actually, by Zoran Bartels, who used the linearization about the approximate solution to prove a posteriori bounds for the Ginzburg-Landau, which is a vector form of the Allen-Kahn equation. And this was further refined by Bartnes, Müller, and Nortel in that paper I told you later, where they just added this assumption and they carried through the error analysis. And also Bartels and Müller in 2012, they used the so-called elliptic reconstruction idea that I'm going to talk about more in a second, to prove L infinity L2 norm. Bounds for the L infinity L2 norm error, for instance. And we tried something with Babis Makridakis in the hope that if we were changing the norm, the dependence, the bad dependence on the small parameter would improve. But we essentially got similar results like this paper. So one key idea here in Bartels, which is very natural, is if you're linearizing about UH, you have to solve an eigenvalue problem. And that's expensive. You don't want to solve an eigenvalue problem for every time step just to estimate your error. However, this is really what makes this work as a practical algorithm. This will be the coefficient in my ground wall. It's a constant. If I make a 30% error or a 50% error, it doesn't matter, as long as I get something. So it's a constant. So a really rough approximation of that eigenvalue suffices. It doesn't have to be very good approximation. And in practice, this is the case. So this was proposed by Bartels, and we followed this approach. And you can use a basic finite element algorithm to approximate the eigenvalue. So you just take the discrete operator of an elliptic problem, and you approximate the eigenvalue. And that is your a constant in your a posteriori error bound for the Allen-Kahn problem. So I'm assuming from now on that this is a solved problem. But of course, this requires some work, but it's not, the complexity is not there. Now, of course, there are so many nice works, so what can we add? Our hope was to take this dependence the stiffness, to take the dependence, the polynomial dependence on this parameter, to take it even lower, to try and make it as practical as possible. And to do that, what we wanted to do is to change the norm. Okay? And the first observation here is that this is an energy, Ginzburg-Landau energy. So this is an H1 norm, and this is an L4 norm. It's u to the third times u integrated. So the idea was, I mean, this is a positive definite term, this is a coercive term, so why not try and prove a posteriori bounds in this norm? It's weaker, but morally not so much weaker as a norm. So this idea was first Kostas Xafinos came up with this idea where he proved a priori error bounds with reduced this epsilon dependence in the power, reduced power than what was known in the L4 norm. And there he used some very complicated duality arguments whereby borrowed from his area of research, which is PD constraint optimization. Okay? So this was like duality theory for a priori analysis of the discrete problem. We don't have this hope in a posteriori analysis, so we had to do something else. Because the plan was, okay, let's try and prove a posteriori bounds and see if we get better dependence in the L4 norm, and that's the challenge. Okay, so this work has two parts. The first part, we did everything for the plain vanilla scheme, which is backward Euler in time and standard conforming finite element method in space of any order. And the second part, we tried to push the boundaries, and we did it for arbitrary order time stepping using this continuous Galerkin method. And in space, we have again this continuous Galerkin method on arbitrarily shaped elements. So these are the two contributions of ours, and of course in the L4 norm. So let me start the technical part of the talk. So let's take the problem, partition the time domain into intervals, and I'm assuming that I have an approximation by a finite element method on each time step, and of course the space may vary, otherwise I'm doing nothing interesting. And this is the basic backward Euler implicit, you see this is implicit, method. It's fully implicit. I'm not linearizing at the moment. Okay, of course you can look at this problem. This is written in weak form, but you can look at this problem in strong form. So this is your stiffness matrix. This is really, these are projections. So you just look at this as an equation of vectors. Okay, and that's useful for the analysis. That's why I put it there. Now, the first observation is that L4 is weaker than L2H1. So I need to use some form of duality. I need to be able to use some pivot to go lower in the Sobolev scales. And also a technique that was developed quite heavily, in Crete in particular, by Babis and collaborators, Riccardo Noceto, Omar Lakis, and others, is the so-called elliptic reconstruction. So what do you do there? So this is the dual of the elliptic projection idea we have in finite element analysis. And what is it that one does there? Well, you look at the discrete solution at one time step, and then you ask yourself, what is the exact solution? What is this discrete solution approximation of which elliptic problem is this a discrete solution of? Elliptic problem. And of course, this is not unique, so you can add all some other crazy terms that help you in your each endeavor at hand, because if you project those two, they will look the same on the discrete space. So it's not unique, but the idea is that you relate the approximate solution with the solution, exact solution of an elliptic problem. And because this is an orthogonal projection in the respective inner product, which is here is the H1 inner product, what happens is that you have immediately that this is a numerical solution and this is an exact solution of an elliptic problem. And for elliptic problems, you have masses of computable error estimators. So you can just take one off the shelf. This is crucial. So we don't need to estimate this error. That's the whole point. Well, the second thing you need to do is you need to reconstruct. So you have time instances, but you need to put the discrete solution into your PDE. So you first have to lift it into some continuous space. So you take the linear interpolant at each time step, and of course the time derivative of the linear interpolant is just the difference that you have. And then you take all these elliptic reconstructions and you take the linear interpolant of those, and let's call it omega. And then you take your error, the interpolated error, and you break it into 2 points, 2 parts. The elliptic error, which is something you hope you know how to deal with, because this is numerical solution of an elliptic problem, and this is the exact solution of an elliptic problem. And a continuous quantities, a difference of quantities, this is in H1. Well, for this, we need an equation. So it's very easy. You sit down and you write the respective error equation for this. So this satisfies a PDE, which is very similar. It's a linearization of what you started with. So the idea now is let's do stability analysis for this. If we can get stability estimates for rho by norms, by quantities that I have on the right-hand side that are computable, I'm done. That's the idea. Okay, but I want L4, L4 norm. So how do I get L4, L4 norm here? That's the key question, okay? So here is my error estimates. If I test with rho here, I will get the standard L2, H1, L infinity, L2 estimates. How do I get really L4, L4? Okay, and this is a non-standard argument. So you test with this function instead. Don't ask me why. Okay, it took a while. So maybe this is known in the PDE community, but certainly we couldn't find it. So you test with rho plus a construction that is like the integral of rho square. This may look very random, so this is what you test with. V is equal to phi. Why? Well, what happens is that if you take rho t comma phi and you just do some integration by parts, what you end up with is something that is tameable plus an L4, L4 norm. So this is very interesting because we have an L4, L4 estimate. And then the structure of this is more or less the same as before, so we can use still the spectral estimate, and that's very crucial to get the complexity down. So we take the spectral estimate, the 5 or 6 pages of Sobolev embeddings and Galliano-Dierenberg inequalities. You need a fantastic PhD student like Dimitra to do this very well and get as much meat out as possible, and this is what happened, and you do some sort of bootstrapping, continuation argument. And if you do all that, you get into a result like this. So, assuming that this quantity, which I'm going to show you later, this is a computable quantity, these are my estimators, is small enough in a particular sense. So when I do a posteriori analysis, my complexity comes into making me be very, very close to the exact solution. So that's my complexity barrier. So it doesn't come as a negative power of epsilon, but comes into my constraint, into my condition. So assuming that this is satisfied, then I have an L4, L4 estimate for rho plus with some other norms. And this norm here is estimated by computable quantities. Now let's see how this works. If we assume that we have this spectral estimate that my minimum eigenvalue is integrable, so it's like have m topological changes. If that's the case, I'm not assuming it because I'm solving. I don't need to assume it a priori. I'm just saying that if that's the case, then my condition scales like e to the m plus 2 plus a half. I mean, this Galliano-Dierenberg scaling. So this is practical, okay? And then this is an estimate for rho, which is half of my error. Okay, this eta looks like this, but it is all computable. Okay, it's complicated, but it is all computable. It's just residuals, essentially. That's what an a posteriori estimator is. It's just residuals of known quantities. Then you can do triangle inequality, and you get an L4, L4 bound for the error, which is what you had before, plus the aspect of the elliptic part under the same conditions. And because the norm was, the analysis could cater, we got L2 H1 estimates and L infinity L2 estimates for free. And in fact, they're slightly formally, I don't know in practice because the estimator is different, they have less dependence on epsilon in the condition than known estimates. Okay? And the higher the m is, the better estimates they are. Okay. So let's go to the second part. I just need a couple of minutes. What we really want is to extend all this to a numerical method that is able to take any arbitrary shaped element within reason in time and then in spaces of any order. So we took a dissipative method, discontinuous Galerkin method, and we have developed over the years a framework of extending the application of discontinuous Galerkin methods into arbitrary shaped space-time elements. Okay? So we're just going to piggyback on that, but we need to prove a posteriori estimates for this general setting, for elliptic problems at least, to get this going. Okay, so the assumptions on the mesh is that basically that I'm star-shaped with respect to a ball. Any element that has this assumption works. Okay, so can do very general things. And because I'm discontinuous, I don't need to match the boundaries, so I can have any shape I like. Okay, so I just have piecewise polynomials on really funny space-time pieces. Okay, this is the space-time DG method, and I will continue complete with this. And from that, we get exactly the same estimate as we got for the backward Euler method. So it's really the same. Just numerically to see, because I don't have a lower bound, the bounds are very similar. Because I don't have a lower bound, this is just a study that my estimator is actually goes in the same order of convergence as my actual error on such a refined sequence of refined polygonal grids, and this is the case. So it works. Okay, so formally, new L4, L4 estimates for various classes of crazy methods. Now, just one sec, if I have 1 minute, no? 2, okay, thank you. I want to say something about Vassilios. So, personally, for me, Vassilios has been I was not a student of Vassilios, but his teaching of numerical analysis made me want to know more of numerical analysis. So I took choice courses, and when I went abroad for graduate studies, numerical analysis always stayed in my head. And that, for me, is something that changed my life. One thing that was mentioned, I think, briefly, but I want to give my personal account, is the books that Greek students are very lucky to have. This is by Giorgos Akrivis, who is sitting here, and Vassilios Dougalis. And these are the books that I learned numerical analysis from, and I still use to this day. This is for basic numerical analysis, and this is the book I teach with at NTUA, and this is for differential equations. And this is what they look like today. Okay? So one thing also I wanted to say is that Vassilios was very keen that I stayed in Athens for my PhD, and he was trying to tell me, you should stay here, he was very proud of his Solaris machine. He was showing me his Solaris machine. But I was very adamant of going abroad. And I wanted to go abroad for the experience, and because I thought, it's good to live, somewhere else as well. So I ended up doing a PhD, and one of the first papers I was given to read was a paper called A Class of Non-Conforming Numerical Methods by Garth Baker. So Garth Baker was Vassilios' academic supervisor. And so Vassilios kept influencing me by giving me reference letters and helping me with his always good advice over the years. And for that, I thank him very much.
Thank you. We have time for one question. Yes.
Very good question. We're thinking about it. So similar things work. So the formal aspect of this nonlinear energy argument works, but you need a gradient, an extra delta. I know, okay, I know what you mean. I know what you mean. Okay, that's, yeah. That's why I said the formal aspect, I can get funny norms, but it's a much harder problem. Because a fourth order operator numerically, you have the square of the condition number. Canhillier is a very painful thing to actually say something very meaningful in this adaptive setting with high. But it is something we have been looking at, yes. Thank you, Nico.
Okay, so let's thank Manuel. So I welcome our second speaker in this session, Professor Stratis from the University of Athens. He will talk about the Steklov-Eigen problem.
So, good afternoon to everybody. It is, okay, first of all I want to thank the organizers, Yorgos, Babis and the two Dimitris for the invitation and for organizing this special event. And it's not only a pleasure for me, but I feel privileged to be here for this special event. Now, I had known of Vassilios since the late 1980s, but I first met him in 1993, when he was already professor at the National Technical University of Athens. At that time, the undergraduate course Numerical Analysis 2, which was numerical analysis of ODEs in my department at the National Kapodistrian University of Athens, was taught by a colleague from the computer science department who took a sabbatical. So I was asked to teach the course. And the first thing I thought was to go and meet Vassilios, with whom I had never met, and ask for advice. And I did so, and this was, you know, the first, our first meeting that went up to 1.5 years ago. Now, I taught this course for 2 academic years, then Vassilios moved to our department and he took it over and did many, many more things about the topic and all this. Now, let me say some things about Vassilios and about Vassilios in Athens, in the University of Athens. In 1999, together with Vassilios and with Dimitris Mitsoudis, who is here, we decided to translate, and it was published by the University of Crete editions, the book Applied Mathematics by Logan. And this was, I think, the first book on applied mathematics that appeared in the Greek language, and it had an impact, and it still has, I think, around. Since 2002, we moved in a new building of the mathematics department, and then since then, until his retirement, and not only, we were in adjacent offices, so we had a very, very closed, everyday, let's say, contact. Now, with Vassilios, with Nika Likakos, and with a couple of other colleagues, we comprised a committee that made some, at the time, important changes, practically introducing a direction of applied mathematics in the curriculum of the Department of the Studies, of the undergraduate studies. And more or less at the same time, it was introduced an MSc program in applied mathematics. And the same committee more or less ran that, and both of these committees were chaired by Vassilios, and he played an essential role in the success of both these endeavors. He had a number of PhD students in the University of Athens. The two Dimitris are here. There were some others, I don't see them, I think, right now in the room, but there were some others yesterday and today present here. And with Vassilios and with Nikos and with a couple of other colleagues, we organized and ran a series of conferences since the first was in 2006 and the last in 2018 that were every 3 years. And this was, I think, a nice series of conferences, and many of you, personally, I had the pleasure to meet during these conferences as guests that were in different and usually nice places in early September in Greece. Okay, since Thursday we heard a lot about Vassilios, but I feel I need to say a couple of things. First of all, I feel somehow obliged to add some things or to repeat some things, but not many. So, okay, as we all know, he was a top-class mathematician. He was an exemplary and award-winning teacher and a formidable mentor. He was a serene and respectable and highly appreciated colleague, characterized by frankness and gallantry, always to the point, often laconic, and never, contrary to many, a conservational narcissist. Vassilios was pertinent and insightful, a highly cultured person with a unique sense of humor. And last but not least, he was a dear friend to me that I miss a lot. Okay, now. Το καλοκαίρι του 1999 που το μεταφράζαμε, το κομμάτι που μετέφραζα εγώ ήταν το καλοκαίρι ακριβώς πριν γεννηθεί ο γιος μου και σε φάση προχωρημένης εγκυμοσύνης της συζύγου μου, εγώ μετέφρασα, ας πούμε, ως δημορής, γιατί θέλαμε να το βγάλουμε γρήγορα. Τέλος πάντων. Λοιπόν, so let me go and present what I intend to do. This talk is based on joint work with Pier Domenico Lamberti from Padova and with Francesco Ferraresso, who is in Sardinia at Sassari, and Lamberti. And it's about a Steklov problem. So I'm going to have a rather long, I would say, introduction about the problem, just for people who are not close to this area. So these are 3 different photos of Steklov to see how he progressed in time. He was not only an outstanding mathematician who made many important contributions to applied math, but also an unusually bright personality. As we know, the Mathematical Institute of the Russian Academy of Science in Moscow bears his name, and there is a very, very interesting and nice paper written by these people in 2014, under the title The Legacy of Vladimir Andreyevich Steklov, which is very, very interesting. Now, for his master's thesis, he worked on the equations of a solid body moving in an ideal non-viscous fluid. There were 4 cases to be considered. 2 of them were solved already by Klebs, an important mathematician. Steklov solved the 3rd case in his thesis, master thesis it was, and the final case was solved by Steklov's supervisor, Lyapunov. For his doctoral dissertation, he worked on problems that arose in potential theory and other areas like hydromechanics and electrostatics, but it was a rather rigorous analytical study. Then, after obtaining his PhD, he studied boundary value problems of Dirichlet type, and with the intention to solve Laplace's equation on the surface. He wrote a book with the title General Theory of Fundamental Functions, which was very important for many years. And the term fundamental functions was introduced by Poincaré, was used by Poincaré, and it means eigenfunctions in today's terminology. And he wrote, he did some work as well on the history of science, and he was an invited speaker at the International Congress of Mathematicians in Toronto in 1924, so rather a big personality. What is the classical Steklov eigenproblem? Is that problem S there? So one looks for a harmonic function in omega, which is a sufficiently regular, let's say at least Lipschitz bounded domain in Rn, and satisfying this. So there is the spectral parameter on the boundary condition. And so, okay, U is called the Steklov eigenfunction, and lambda is called the Steklov eigenvalue. Although it is nowadays known only as Steklov's problem, it seems that already, and he introduced and studied it in 1902, Poincaré, as in many other areas, he was already before in that problem, in 1896, in relation to tidal waves. And Hilbert himself worked in similar questions a bit later in 1912. It is interesting maybe to mention that the full, let's say, Weyl asymptotics for the Steklov eigenvalues in n dimensions for domains with Lipschitz boundary was very, very recently justified, earlier this year only. So this Steklov problem can be considered as the eigenvalue problem for the celebrated Dirichlet to Neumann map. Okay, I will not say many of these details, which are not details, in fact, because I already made some introduction, there's not much time. So if one defines a map from h half of gamma to h minus half of gamma, gamma is the boundary of omega, by this relation, this is the Dirichlet to Neumann map. The Steklov problem has a really broad variety of applications. I mentioned some here. So one of them is the famous Calderon problem, which is the inverse problem of recovering the electric conductivity of a body from the knowledge of the voltage to current map. Another area is the so-called spectral geometry, which is a modern area, very important and very fruitful. Then about shape optimization, about general second-order elliptic operators, the generalization of the classical problem, differential forms on compact Riemannian manifold with smooth boundary, the biharmonic equation, going to higher order equations, linear water waves, vibrating membranes, and Earth surface effects, and the so-called silent earthquakes. And a bit to my surprise, there is an interesting paper about maximizing the information transmission rate in the cerebral cortex, and this is another version of the Steklov's problem. Okay, I've written some things here, but I'm not going to read for you or to comment on them. About one or two of these problems I mentioned before. So if one considers waters in a canal or open sea or unbounded domain, and then it is of interest that one ends up with a typical Steklov problem. And there are many papers, but the important one is by Nazarov and Taskinen in 2010, where they showed that the continuous spectrum may be non-empty even in a bounded three-dimensional pond. And they studied a lot. there is this book that I like a lot, but most of you here know much more than I do about water waves, etc. So let me move to another problem, the famous sloshing problem. This is the problem of studying of small oscillations in a liquid. And this is a problem that it is, let's say, a special case of a boundary value problem of the type studied already in 1955 by Miranda. But there are much more recent than 1955 results by Canavati and Minzoni that under very special assumptions, they reformulated the Steklov problem in terms of a non-local operator, and they got very interesting results. And these problems are very similar to regular Sturmy-Will problems. A typical application is, the linear coffee waves. If you have a cup of coffee and there is liquid sloshing, then the velocity potential satisfies this problem. And if you separate variables, you get a typical, this is a typical Steklov boundary condition. And okay, you have Neumann on the bottom. Now, let me say another area which is very important in relation to Steklov problem. It holds some surprises in shape optimization. For example, is it very well known that the Faber-Krahn inequality states that among all domains of fixed measure, the first Dirichlet eigenvalue is minimized by a ball. The corresponding problem for the first non-zero Neumann eigenvalue is the so-called Sergei-Weinberger inequality, and says that this is maximized by a ball. And and these are just like that, the statements, so not topological assumptions. If one considers the analogous result about Steklov eigenvalues, is the so-called Weinstock inequality. This states that among planar domains with fixed perimeter, the first eigenvalue is maximized by a disk, provided that omega is simply connected. So it's topology enters now. And in fact, the asymptotic distribution in this case is much, much more highly sensitive to the regularity of the boundary than in the classical Dirichlet or Neumann cases. There are a number of numerical approaches and techniques that I've written, and the majority in this room know much more about me than me about them. But anyway, it might be of interest to some of you. And so let me go to the actual part that I would like to present. How much time do I have now? 12 minutes, okay. All right. Okay, so we are considering time harmonic Maxwell equations. So the fields are of this type, and these are the typical equations. And we consider that the permittivity and permeability are constants, real constants. So therefore the fields are divergence-free by Maxwell's equations, since these are constants. Now, in this formulation, electromagnetic metamaterials can be entered into the problem. These choices of the sign of epsilon and of me describe the dielectrics, the so-called gyrotropic materials, plasmas, and left-handed materials. And so, I mean, they are, in the case that at least one of the two parameters is negative, we are in the field of metamaterials. Now, okay, if we consider the interior problem, this interior problem for the electromagnetic field, the interior Calderon operator is defined. It's something similar to the Dirichlet-Neumann operator, and it's defined as the mapping of the tangential part, tangential component, let's say, of the electric field to the tangential component of the magnetic field. So it's such a thing. These operators are called as well Poincaré-Steklov operators. Some of the history I told you about this terminology. But depending on the scientific, let's say, society in which they are studied, they are also called impedance or admittance or capacity operators, mostly in the electromagnetic community. If we eliminate the magnetic field, we get this boundary value problem. And we consider a variant than the usual, let's say, interior Calderon operator that was used by Cessna in 1996 in his famous book. And we had studied with Christensen, Velander, and Giannakopoulos in another setting. So we consider a variant that is more convenient to our purpose. And so if so the corresponding problem is this. The corresponding, let's say, Steklov problem in electromagnetics for Maxwell's equation is this. So it's a double curl. K square is the wave number in the case of dielectrics. And the following, okay, the comments written here, the boundary condition is this, where E sub t, where have I put it here? Yeah, where E sub t is this vector field. So this is the typical Steklov eigenvalue problem in Maxwell's case. Now, this problem for positive K was introduced 5 or 6 years ago by Camagno, Lachner, and Monk. And they pointed out that the spectrum is not discrete. And for the case of the unity ball in R3, it turns out that there are two sequences of eigenfunctions. One is divergent and the other converges to 0. And they modified the problem in order to overcome this, let's say, difficulty. And then used it for the study of an inverse scattering problem, studying what is called the signature of a scatterer in this setting. Now, with Pierre Lamberti in our first work, we consider that problem, but we consider it for not necessarily for positive K, so we allow metamaterials as well, and most importantly, we consider tangential vector fields, in which let's say, setting, it takes that, let's say, much more classical look. It's completely let's say, the corresponding problem to the classical Steklov problem. Although, as I mentioned about the Steklov problem, there are many references by some of them by many important people in many let's say, areas. Some of them I wrote before. For Maxwell's equations, there are not that many, and they are rather recent. Practically after 2017, by the paper by Camagno, Lachner, and Monk I mentioned, there are publications by Ciacconi, Kogar, and Monk, by Kogar, Colton, and Monk, Kogar, and Monk, and by Hala. Incidentally, Kogar is the only joint PhD student that Colton and Monk, although they have been collaborating for ages, they had rather recently. Now, okay, so our energy space will be the space x sub t up there. And now we consider, we want to guarantee coercivity, and in order to do that, we use a kind of an old trick by Costabel and Dawes. We introduce a penalty term, theta grad d view, where theta is any positive number. So we consider this eigenvalue problem here. And as I mentioned, we do not assume that this is necessarily positive. So we consider that we interpret in the weak sense the problem as is written there in this relationship. And we need to assume that k squared does not coincide with any of the eigenvalues of this problem here. Let me just say what I've written here, is that these two boundary conditions, in fact, are this, because, okay, these are the two components of the electric field, so in fact, this is the problem. And this has a discrete spectrum, which consists of the sequence of positive eigenvalues of finite multiplicity. So, the assumption that I mentioned before is that k square is different than all a n. The first eigenvalue, we have a characterization very similar to what Manolis mentioned before. And the result is for the case that k squared is less than a1, and I will make a comment for the more general case a bit later on. So the result is that if k squared is less than the first eigenvalue of the problem I considered before, and theta is positive, then the eigenvalues are real, they have finite multiplicity, and are represented by a diverging to minus infinity sequence lambda n, and lambda n, and therefore, so we have a min-max representation for every eigenvalue of this form. Now, okay, let me say, I will skip some of this material, but let me say that we can decompose our energy space as practically H10, okay, to the third, they are fields, plus H omega, where H omega is the orthogonal complement of the kernel of that operator mentioned in the first upper part of the slide. And in fact, this H calligraphic is the full analog of the role that the harmonic functions play in the standard, in the classical formulation. Okay, yeah, I understand. Right. So, okay, the general case is when k squared is between consecutive eigenvalues. It is more demanding, more technical. The proof, anyway, I didn't present any proof for the simpler case, but it's done there. Right, now, let me say a couple of remarks. If we consider the set of eigenvalues of the problem with the penalty term, and we consider these green and red auxiliary problems, the first is a typical Neumann problem, standard Neumann eigenvalue problem. The second is the so-called magnetic eigenvalue problem. So that's why this is superscript is there. And there is another result which is interesting that says when k is non-zero and theta is positive, then 0 belongs to that is an eigenvalue if and only if k squared in fact has such a decomposition. Okay. It is not a decomposition, but it's either a theta multiple of the Neumann eigenvalues or a magnetic eigenvalue. Now, okay, there are some things I'd like to say, but there's no time. One is that this kind of, let's say, studying the structure, the eigenvalue set, is important, but because one can expand the solution of the problem in series in terms of these eigenvalues. And not only this, but one can represent the trace spaces in terms of these eigenvalues. And this is much simpler than using, let's say, the definition of the trace space, because it's okay, you cannot compute it in this way. And then I'm not going to say anything more, although I'd like to, because it's the special case of the sphere, in which case, let me only using, sorry. So there is this theorem that in the case of the ball, of the unity ball, and if k is non-zero, real non-zero, then the eigenvalues are given exactly by these two families, and the corresponding Fn, the eigenfunctions. And both the families diverge to minus infinity, and Fn are non-divergence free, while En in the second sequence are divergence free. And, okay, And okay, and a remark is that the denominators appearing in both these cases upon our assumption, our standing assumption, they are non-zero, so we don't need to make any further assumption. And that they coincide in the case that theta is 1 and k tends to infinity with values computed by Rollo and Savot in their study of the spectrum of the Dirichlet-Neumann operator on forms at Euclidean domains. And excuse me for taking a bit extra time. Thank you very much for your attention.
Maybe we have time for a quick question. What happens for metamaterials? Is there
What happened? I mean, the result is the same because the result is the same because it holds for all these combinations. So even in the special case of the ball, etc., I mean, the calculations, which are not numerical as you saw, but they are using special functions and spherical harmonics, etc., are the same, have the same form. So, okay, we have not made any views of this, but it's an interesting remark, I think, because it applies, we are not restricted to the sign of epsilon and mi by the sign.
So our last speaker for this session is Nikos Kampanis. Who will talk about local atmospheric and wave models.
Thank you, Chrysula. Good evening to everybody. I'm fine here. I will not discuss it for Vassilios and our relation and our work in advance. I will wait after the talk if we still have time, so I will not violate the schedule. In the meanwhile, I will say a characteristic word. I will sail you to some more technical things like data, like large-scale computations, but with environmental models where all this, or this very formal error estimate are not applicable most of the times. So it's quite difficult to say which one is better than the other. I have done it. I have done some efforts on this, and I expect to convince you. So, what is the purpose of all this work? Several years now, we got some funding from the marine services of the Copernicus to beat the Copernicus resolution locally around Crete. This is something that the marine service of Copernicus and also in general Copernicus is doing in specific areas when you can convince them that all this improvement of resolution is necessary. For example, here in Crete, around Crete, to have more resolution in the forecasting of oceanographic models is significant because you have to deal with a complicated coastline. You have to deal with islands that sometimes prevent the weather to express himself as it is in the North Aegean, for example. So one question is about how you make more accurate the wave model that we are running, because there are reasons you need that. For example, if you want to go within a port, there you have to go down to resolutions of 100 meters, even less, while the standard Copernicus data are 27 by 27 kilometers approximately. Another also significant reason to increase the resolution for the wave model, apart from the wave model, is the meteorological model. What is the need to do it, to do the waves in a small cell, in a grid with small cells, when you use meteorological data from coarser grids. So we used, beyond the models, we used the data that come from the NOAA coastal meteorological stations, and also data from some buoys of Poseidon system of the Hellenic Marine Research Center. But they are not current, they are hindcast because these buoys are the closest to Crete, are not in function several recent years now. So let's see here. Start then with the meteorological model. The meteorological model is the WRF, and we initialize this initial at boundary conditions starting from the GFS model. We have to go from 27 kilometers by 27 to grids of 3 by 3. This is the resolution we have decided is quite enough for general purposes around Crete. We start then the WRF. We use specific data. You see the products, I don't read them. You can see it's complicated to spell. Just remind that it is 27 by 27 kilometers. So this is the grid, the largest grid, the 27 by 27. We start with this, then we downscale to 9 by 9 kilometers. The grid is not only this one you are seeing, it's beyond the limits of the graph here, but the significant grid, which is the 3 by 3 grid, is shown here. So within the small frame here, we are doing all this for oceanographic, meteorological, and then oceanographic forecasting. So these forecastings we are trying to improve, not only by diminishing the grid, but also assimilating data from in situ data. So one first remark, you see on top how the GFS model in 27 by 27, or it is the 9 by 9, I don't know. Let's have it as it is, and then we see the WRF we are computing in 3 by 3 cells, how the resolution is better and more realistic, because all this red for the specific case we are showing here is not the best approximation. Let me now introduce some metrics we use to see which one of the result is closer to reality. Here you see the result of the calculations, the computation. Our results are the gray and yellow. It's the bias WRF, first, second, and then the yellow, with different metrics. The one is mean value, the other is mean squares. The shortest the column is, the better the results are in comparison with the reality. So at first point, 3 by 3 beats the 27 by 27. And here we are doing some other grid techniques, the grid nudging technique, to improve the accuracy of the WRF model we are running using Copernicus forcing. You see that we have the R5 from the Copernicus data, you see the line, and then we have various choices of WRF runs regarding different type of initialization. We get the forcing, and then we use different algorithms to to map the Copernicus data to our grid so we can forecast. You see that only in the last case, it's the last case is better than the case with the blue. So grid nudging seems to be a technique that helps the model to better capture the conditions, to assimilate the, to capture the meteorological conditions. Oh, okay, thank you. So let's see then what we have functioning operation in the lab. We start from the wind model. We start from the wind model. We start from the wind model here. We start from the wind model here, and then we go to the wave model. Keep in mind this graph, because later we will see how we can even this one with high resolution to improve it. The test case is in Crete, so we take the result of our wave model, and we have two buoys selected, which are the nearest for Crete, one here, just outside the port of Heraklion, and one farther near in the open side of Santorini. This is just point-wise comparison. It is similar. I just say this. Now, how we can take all this real data measured by the buoys and assimilate them in our model? Very complicated formulas. Here we correct our forecasting on the buoy, the one of the two, and then using selections of coefficients which depend on how much we, what percentage we believe, at what percentage we believe the data is correct regarding the forecasting. So we do this for the, we have several selections for the coefficients here depending on this assumption. Then we compute, we correct on the buoy, and then we use it to correct the whole grid. You would say, oh, 1 point will correct the whole of the grid. Let's see the next then. I skip all these are different choices of the coefficients regarding the expectations of which one of the two is better. And see this. We have the original model. I have seen you before, the wave model. And you see how this is corrected when we use assimilation data from this buoy here. It seems that the whole forecasting is corrected, especially in this area, although when we go farther from the point of real data, the forecast remains more or less nearer the original one. Here is a video. And here is, on the right, a comparison. The blue, the red is with assimilation, the blue is without. The blue is with, the red is without. So, a lot of computations a lot of formulas used to interpolate from the coarser grid to the fine grid. We get better result as the indices have shown to us. And then we just take 1 point from 1 point real data from one site, and this correct a significant part of the domain, in a significant part of the domain, the computation, the forecasting. The more points we will have, the better. And if they are distributed evenly throughout the domain of interest, then this definitely will improve the forecasting, the quality of the forecasting. And new, couple of weeks ago, we were in the we were happy to install our own wave meters and current meters. They are placed in the lee side of the water wave, the break wave of the port of Heraklion, near the entrance. And we have started to have our own time series at the point. We have just one point, but we have 3 levels, which is important because we monitor all the column of the sea, and this is also significant. And we hope to be able to install others. We prefer to install them near the coast because along the coast is where we want to improve, because along the coast the computation is more tedious, more difficult to do. You need to approximate the coastline and also have the model to imitate the wave behavior as closely as possible, because there you have, beside the sea conditions that you have to transfer, for example, to people that use the beach for safety, for leisure, you can relay them to people that are to stakeholders of the coastal sea areas, or even farther. Like fishermen, like the liners going from Crete to Piraeus, or the cruisers that arrive to the port. And there you want to have digital services for them that they need to use high resolution forecasting of the wave of the sea state, I would say. And don't forget that beside this, we have an actually operational weather forecasting model with low resolution, with high resolution, higher than even of that of the Hellenic National Meteorological Service. And just to tell you that we are going to apply this to a specific area in the east part of Crete where surfers are using the area for their sports, and there we expect we will install at least 2 or 3 meteorological stations to monitor the local conditions as accurate as possible, and we are expecting to go down to less than 50 meters of grids. Thank you very much. This is something that all these techno-bubbles, I would say, computation, it seems to be like 15 years at least before today that we were discussing with Vassilios, and we were saying we have to do something in environment. This period was the period that most researchers doing forecasting, simulations, wanted to apply their work and do research in environment. We were going from land to atmosphere, but as native Cretans, living close to sea and liking the sea much better, much more than the mountains, for example. We eventually arrived to work with wave models, hydrodynamical models actually, that forecast the sea state, the currents and waves and so on. And we have established the Coastal and Marine Research Lab in Forks in IACM. Thank you.
Thank you. Are there any questions? I have one. So I have seen, I think, work by Nathan Kutz on how to place optimally these buoys. Like if you wanna optimize the prediction in some area, where should you put the buoys?
Should be something of most important. It is actually of most important, but it's difficult to find buoys exactly the place that you want to have them. For example, I put them on the wave breaker of the port of Heraklion in a certain place, which is near the port, so I control the port, the entrance of the port, but actually the place is quite difficult because you have all this breaking of waves, the swell, so you can have extra effects there. So the measurement sometimes is not quite exactly what you want to measure. Not false, but not exactly what you want to measure. Anyway, it's difficult to find buoys because real buoy, an operational buoy for operational work is quite expensive, quite difficult to maintain. We are trying for this. We hope sometimes we will be able to have one. One is quite good. If we could have an array, and actually not, because those that we have installed in the port, they are low-cost sensors. But all these buoys, you can go up to, say, between 50 and 100,000 euros. You can have satellite communication, so you don't have to go there every time, so on. An array of 4 or 5 would be enough for Crete. 3 at the north, in the south, because north is more developed. The area, the coastal area of Crete is more developed in the north, less developed in the south, and you have less area where you can reach for enjoying the sea, recreation, for business, for whatever.
Thank you. So let's thank Nikos again.
You can sing this forecast before I go to the sea.
So let's thank all the speakers of this session, and we can get some coffee before our last session.
And our first speaker is Michalis Dougalis, and he will speak about forward and inverse problems of underwater acoustic propagation.
Thank you, Mr. Chairman. Before starting, I would like to thank the organizers of this conference for giving me the opportunity to be with you today in honor of Vassilios Dougalis, a great friend and a great collaborator. And it is also an honor for me that the session is chaired by Kostas Dafermos. He's a very well-known mathematician with so many contributions in all the areas of mathematics that I feel very honored to be chaired by Kostas Dafermos. So thank you very much for the introduction. And when I gave the title of my presentation to the organizers of that meeting, I said, okay, I will talk about the IACM fourth experience in underwater acoustics, which, as Kostas said, was actually introduced in this institute by the late Professor John Papadakis. But then I realized that that was a very ambitious goal, because all what we have done in underwater acoustics cannot be contained in a talk of 30 minutes. So I changed the title of my presentation to be a sample of the IACM fourth experience. So I'm going to present some of the approaches that we have applied in our institute to deal with problems of underwater acoustics. And my presentation will be in a modular format, so if I'm running out of time, I'll stop and move to the last page, to the last slide. Another important aspect of underwater acoustics is that the area was very much led by Vassilios Dougalis. When I came here in 1988, I started discussing with Vassilios about underwater acoustics, and he showed great interest for both the theoretical and technological aspects of underwater acoustics. Then we started discussing about what we can do in wave propagation modeling, in the numerical analysis of problems which are related to wave propagation, especially in underwater acoustics, and also to technological challenges. So he supported, along with John Papadakis, the creation of the laboratory of underwater acoustics, which is now very active with very many applications in the real world. So Vassilios Dougalis decided to join me in several of the underwater acoustics conferences that I started participating. And here are some pictures of these conferences. In 1990 in St. Louis, he participated in a session on underwater acoustics that was organized by the American Acoustical Society. And then in Boston in 1991, in a conference again on underwater acoustics. And here you can see Vassilios admiring a drawing by Canaletto. Canaletto was one of his his favorite, artists. And in another museum in 1992 in New York, Vassilios was a lover of arts, of culture. So whenever we had the chance, we would go to the museums in the towns where we had to present some work and visit the museums. And here is in Princeton. You know what this entrance is? Is the entrance of the dormitories that hosted Vassilios during his stay in Princeton. So when we went there for another conference, he said, okay, well, let's go to the dormitories that I used to at that time, and we took a picture there. And this is another picture of Vassilios and Emmanuel Scarsoulis in Portugal during another conference on underwater acoustics. So the outline of my presentation will be to present some characteristic approaches for forward and inverse problems of acoustical oceanography. Just a few cases, as I said. I'll pick up a case where we apply normal mode theory for solving the acoustic equation in range-dependent and 3D oceanic environments. And another topic of forward acoustic propagation model is how we can work with the parabolic approximation. Of course, in our institute, we have used several other approaches, ray theory, spectral methods, finite element methods, etc. But I will concentrate on only these two approaches. So the problem is to solve the Helmholtz equation with a point harmonic source. This is our starting point. And we normally work in a cylindrical coordinate system. So the first point where we started our work here was based on a work that I have done during my PhD, and it concerned propagation modeling in axially symmetric environment, range dependent, with a homogeneity of compact support. So in order to solve this problem, we had to discretize the domain, the homogeneity domain, in several segments, in each one of which we had to define the so-called depth problem, which is actually a Sturm-Liouville problem, non-regular Sturm-Liouville problem, which has a discrete spectrum and a continuous spectrum. And in order to have some solution which is meaningful and easy to be treated, we had to keep only the discrete spectrum, which corresponds to the so-called propagating modes. And here are the boundary conditions which are imposed when we consider fluid layers. So this is some typical results we get from the code mode 4, where we numerically evaluate the eigenvalues, eigenfunctions, when there is a sound speed profile that varies with depth. And I would like to acknowledge the help of Panagiotis Hantsipantelidis, who is here in this area, because he actually created a solver for the numerical evaluation of the eigenvalues in this code, which is a code that is still used in our case. Another example of how we calculate the acoustic field. The colors correspond to the intensity of the acoustic field, with the red color indicating high intensity and the blue color a very low intensity, and they correspond to the transmission loss, which describes actually the acoustic field in underwater acoustics. Then we move to another more complicated case, the case of a sea mount, which is not necessarily in an axially symmetric environment. So this mount can be in a three-dimensional environment, but the results that I'm going to show you correspond to the case of a sea mount, which has some symmetry. So again, we solve the problem with the help of the eigenvalues and eigenfunctions of the depth problem, but then we have also to include azimuthal modes. And this inclusion makes the problem a little bit more complicated, because now we have Hankel and Bessel functions of a higher order. Anyway, this is an example of a master thesis, a recent master thesis of one of my students. It's an indication that we are very much interested in this problem even now. So Saratsis presented the results with a cylindrical mount, as we can see here, and the results correspond now to a horizontal plane at the depth of the source and the receiver in an oceanic waveguide. So these are some examples of problems that we work with, and for solving the problem of the Sturm-Liouville problem of obtaining the eigenvalues and the eigenfunctions of the depth problem, we use the mode 1. And now I present the only presentation that I had together with Vassilios Dougalis and Nikos Kampanis. Nikos is in this room today. It was presented in the Underwater Acoustics Conference in Rome in 1998, and it's a comparison of the coupled mode solution in an environment that you can see here with finite element methods. So at that time, Nikos Kampanis and Vassilios Dougalis worked together to develop solvers with finite element methods for a problem like this. So we had the only common publication at that time. Another area that we worked with is related to the parabolic approximation underwater acoustics, an area that was introduced by John Papadakis. And of course, it is based on Tappert's idea that we can factor out the pressure field, the P, the pressure, the acoustic pressure, using two functions, one function which can be expressed in terms of the Hankel functions and another function which obeys a parabolic type approximation. And the important contribution of John Papadakis at that time was to introduce an impedance boundary condition to treat the interface between water and the seabed. And what we showed later was that if we have an elastic seabed, which was not an easy case to be treated with parabolic approximation at that time, we can formulate the impedance condition in such a way so that it can include also shear propagation in the seabed. The numerical code that we used at that time was based on an implicit finite difference scheme with a fast Fourier transform algorithm to evaluate the integral in the boundary condition. And here is one picture that is taken from the publication in the Acoustical Society of America and shows the results obtained by our code in comparison with the results obtained by the Safari code, which at that time was considered as a nominal, I would say, code to solve problems with elastic seabed. And here we can see the transmission loss as a function of range for a specific source and receiver depth at the frequency of 50 Hertz. So the comparison is very good. What about the use of these models? We use it for the prediction of sonar performance, for modeling ship traffic noise, which is another open project that we have here, and Emmanuel Scarsoulis will present his work in this area. All these models, all these codes are consist of the framework models for inverse problems, and of course we use it for marine bioacoustics. Now I'm going to the second part of my presentation, which concerns inverse problems in underwater acoustics. Chrysula yesterday made a very nice introduction to inverse problems. We worked with inverse problems underwater acoustics in various areas. First area is ocean acoustic tomography. I'll say a few words about that later on, about bottom classification and source localization identification. All these areas are areas of interest and of current research at the Institute of Applied Computational Mathematics, but I will only concentrate on ocean acoustic tomography, which is an area that was actually introduced in underwater acoustics by the famous oceanographer Walter Mank, who passed away 4 years ago at the age of 102 years. Here is in front of the sound sources that he introduced in the 70s for ocean acoustic tomography. And this is one of his last pictures taken with me in Paris in 2018. Anyway, the idea of ocean acoustic tomography is similar to the medical tomography. So we have to install in some areas some stations consisting of transceivers that can send and receive acoustic waves at certain intervals. And these transceivers define propagation paths, each one of which is associated with a vertical slice of the water column. And the idea is that if we have a known sound source sending acoustic waves in this environment, and we have either a single hydrophone or a hydrophone array at some distance from the source, we can exploit all the information that can be retrieved from the signal which is received at the hydrophone array to estimate actually important parameters for the water column, which are of interest for environmental monitoring. And the most important parameter is temperature, the sea temperature, which is associated with the sound speed profile. So if we are able to use these measurements here to identify the sound speed profile in a range-independent or age-dependent case, then we can do it several times in order to find the evolution of the temperature change in some specific environment. And later, we also introduced, as the unknowns of the inverse problem, the geoacoustic parameters of the seabed. So our institute participated in the first experiments of oceanoacoustic tomography that were held in Mediterranean Sea. The first experiment in the Gulf of Lions, close to the French coast, and the second experiment later on covering the whole Western Mediterranean area. We can see here all the locations of the observatories that we have mounted there with the help of several partners from Germany and France that collaborated in order to actually validate the idea of oceanoacoustic tomography in the Mediterranean. And here we can see what we get from at the station W3, as we can see here, very close to the African coast, with source located very close to Marseille. And this is a series of signals that are measured and are analyzed thereafter to infer the temperature evolution from November 1994 to February 93 to February 94. Anyway, this is one of the first experiments that we have conducted, and these experiments actually motivated our further involvement in several other problems of oceanoacoustic tomography, because at that time, and Emmanuel Skalsoulis knows it very well because he was deeply involved in the analysis of these results, we have used the so-called ray theory and the analysis of the peaks of that signal using also the notion of peak arrivals. I'm not going to talk about that, but the idea is to try other approaches for oceanoacoustic tomography that could potentially work. So what we can do with the available instrumentation, we can use either an array of hydrophones, in which case we have the possibility to exploit the spatial structure of the propagating modes, or to do mode filtering, in which case we can extract the modal phase. So one of the approaches I'm going to show you later on is based on the modal phase. If we have only a single hydrophone, which is the case in most of the applications due to cost reasons, an array costs a lot, and whereas a single hydrophone is less costly. So what if we have only a single hydrophone? So having a single hydrophone, we can have ray arrivals, as it was the case that I showed you before, or we can identify modal arrivals, which is the equivalent of ray arrivals when we consider that a mode propagates at a specific velocity, and then it comes to the receiver at a specific time. So if we are able to identify modal arrivals, we can exploit this information in the framework of a linear inverse problem. And another possibility is to do some post-processing in the signal and get the dispersion characteristics and identify the dispersion curves that describe exactly how modes propagate in the environment. This is time frequency analysis. And lastly, we are using statistical characterization and the probabilistic means in order to characterize the signal and eventually invert for the unknown parameters. About the modal phase approach, which actually is an approach which was abandoned by our team because it's not practical. But I wanted to mention it just for historic reasons, because it was one of the first approaches that we have tried in order to solve the tomographic problem. So we can see here with red what is called modal phase. This is the solution for a range-dependent problem, but if we are using the adiabatic approximation and not the coupled approximation that I showed you before. So we have the modal phase, and we can prove that there is a relationship between the variation of the modal phase when there is a small variation of the sound speed profile. So the sound speed profile variation is associated with the modal phase variation in terms of all the other quantities that are referred to some background sound speed profile. So if we know by a priori information that the variation we are seeking for is very close to the actual background environment, then we can do something in order to come up with a discrete inverse problem which is of linear character, but the kernel is not very good. So the condition of that kernel is not very good, and we have a lot of problems in order to get some meaningful results out of this approach. So we had actually to abandon this case, and this is why I said this is just history. And the other approach, which is based now on modal arrivals, is also part of the history as per se, in the sense that also it suffers from problems in identifying the modal arrivals. You can see here that in order to be able to use a formula like this, we have to identify which are the modes that appear in the signal. This is not very easy, although I have introduced a method for an automatic identification of the modal arrivals, but if we don't have many of those, then it is not practical. So we're going to the next step of solving inverse problems in underwater acoustics, which requires the use of an array of hydrophones in order, as I said, to exploit the spatial structure of the acoustic field. And since this is a non-linear inverse problem, which is treated as an optimization process, we have to define an appropriate processor so that its maximization is associated with the solution of the inverse problem. And a standard processor that has been introduced at that time was the Bartlett processor, which is shown here. And the replica fields, which are necessary in order to associate the measurements with the fields taken from a search space on the unknown parameters that we want to evaluate, are calculated using a diagrammatic mode. And the process that we have obtained, that we have adopted at that time in order to solve the problem, is by using a genetic algorithm. It worked very well at that time with simulations, not with real data, because we didn't have real data with an array of hydrophones. But we were able to prove at that time that using mixed field processing, even in range-dependent environments that I'll show you later on, we are able to estimate what we are seeking for, that is the variation of the temperature of the water column. So this is an example of what we can get by simulations. We have a cold eddy here. Here we can see here that the numbers correspond to the sound speed in the water column, but the sound speed is associated with the temperature. So cold color indicates low temperature, and red color, warm color, indicates high temperature. So if we have a cold eddy, like here, this is the simulated real eddy, and we apply mixed field processing in a hybrid way so that we can improve or fine-tune the results obtained by the mixed field processing by using the modal arrivals. We can have a result like this as a first step to the right, and it can be improved by the hybrid approach if we introduce also the notion of the modal arrivals in a way so that the initial eddy is very well reproduced. So we were very well satisfied about that problem. However, it is very tedious to be sure that we are able, first of all, to have an array of hydrophones in realistic applications, and also to be able to identify the modal arrivals. So what if we have only a single hydrophone and try to use the information in the single hydrophone? Now it comes slowly what is related to machine learning, in order that what we have in the reception and the set of data can be characterized in such a way so that the characterization of these measurements are used for the inversion. So we introduced a few years ago the idea of having a statistical characterization of the acoustic signal. So if we have a signal which is measured at a specific location in the water column, we can apply wavelet transform at several levels by applying high pass and low pass filters to obtain the signal at various levels, and then try to find out if the coefficients of the subband coefficients of that signal can be statistically characterized. And we have shown that alpha stable distributions can indeed be used for the characterization of the signal. So we did so, and we characterize the signal with a set of parameters that correspond to the characteristic function of the symmetric alpha stable distribution. We introduced a metric in order to compare replica fields with the measured fields, and this metric is based on Kullback-Leibler divergence, which is appropriate for solving problems where we have to compare probability distributions. Again, we have to calculate the replica fields, and the replica fields have to be also characterized by using the same approach. And we have shown with several publications in this area that if we use denoised and de-blurred signals, because signals can be contaminated by noise or blurring, and we extract noise and blur from that signals, the results could be very good. I think that I have 2 or 3 minutes just to show you an example of these applications. With a test case like this, we have to recover the sound speed profile and the parameters of the seabed. We can see here the actual values, the reference values, the operational characteristics of this simulated case, the search space, and using again some genetic algorithm with 50 generations of 200 individuals each, and applying a signal-to-noise ratio of 10 dB, we can get a result like this. We present the results of the genetic algorithm by showing the a posteriori distribution of the members of the final population. So we can also indicate the best individual, and also we can infer how are the confidence intervals in the retrieval of the unknown environments. Here we can see that when we do some denoising, the results are very close to each other. I mean, the actual value with a recovered value, and in most cases they are enough for our applications. I'm not going to show you some result obtained for a cold eddy again. The cold eddy is used as a reference case for testing inverse problems in underwater acoustics. So I'll say a few words about the future trends of our team, which is, first of all, to apply passive ocean acoustic tomography so as not to use sources which are man-made, but sources of opportunity or physical sources, natural sources, to work with signal characterization and subsequent inversion based on alternative machine learning techniques, and there is already a publication in this area, but also to introduce signal characterization methods in seismic signals. And I want to say just one thing, if I may, 1 or 2 minutes, if you give it, okay? Because a few years ago, I suggested to Vassilios, when he was director of the Institute, to install actually a seismological station at our Institute. The seismological station is now part of the network of seismological stations of the National Observatory of Athens, and we are using the data that we continuously get from this seismological station to monitor the seismicity, which is another very important application. And we have already started working with that, and this publication is referred to the earthquake of Arkallohori that we monitor, and we try to find similarities between the main earthquake, the main shock, and the aftershock. So it was a very nice introduction, thanks to Vassilios, because Vassilios was the person who said, okay, we can now not only concentrate on underwater acoustics, but move also to seismology. And if we are able to do some good work in this area, that would be fine. So I would like to thank him for his support. It was a privilege for me to be a friend of Vassilios. I was in close collaboration with him at Fourth, National Technical University of Athens and University of Crete. For some period, I was a lecturer at the Technical University of Athens while he was a professor there, so we had also a collaboration in NTUA. And of course, the continuous exchange of ideas and energy between us was very important for me. He will be always in my heart and in my life. Thank you very much for your
attention.
Thank you for a very informative lecture. You managed in 30 minutes to present all these accomplishments here. Are there any questions for Professor Dougalis? Okay, go ahead.
Thank you very much.
Thank you. So we close with Professor Alois Kasoulis, who will speak about estimation of underwater noise pollution due to shipping in the eastern Mediterranean Sea.
Pollution comes in the end. Good. Thank you very much. Thank you very much. It's a privilege to be here. I would also like to thank the organizers for this conference, which is an expression of our respect and love for the very special Vassilios. As Michael pointed out, there are many applications of underwater acoustics, and this mainly has to do with the fact that in the underwater environment, sound plays the role that light plays in the atmosphere. Why? Because light and electromagnetic waves undergo severe attenuation in the underwater environment. And here I would like to acquaint you with an application in the initiation of which Vassilios played a decisive role. So some 10 years ago, in the middle of the economic crisis in Greece, Vassilios developed and shared with us the vision for the creation of an environmental data science center at Forth, focusing on application areas such as seismic monitoring and imaging, underwater acoustics, and satellite remote sensing. At about the same time, at the European level, the application of the so-called Marine Strategy Framework Directive of the European Union, abbreviated as MSFD, was speeding up, aiming at the achievement of good environmental status in European waters and seas. And one of the main areas in this directive was ambient noise and noise pollution in the underwater environment, mainly due to shipping. Ship noise is low-frequency noise, dominating in the spectrum below 500 hertz. It is created mainly by cavitation taking place on the suction side of the propeller blades, but also vibrations of machinery and hull cause this noise. And because of its low-frequency nature, it propagates very efficiently over very long distances, and it affects the soundscape, the noise balance, I would say, of areas that are hundreds of kilometers away from major shipping lanes. Now, the MSFD poses very strict obligations on member states, on EU member states, and one of these obligations is the continual monitoring of the ambient noise level distributions over the entire economic zones, the exclusive economic zones, the EEZs of each of the member states, either through measurements or through modeling. And because of the extent of the EEZs, you understand that modeling has a major role to play in order to cover these immense areas. So motivated by this, we discussed with Vassilios and decided to develop a pilot application for real-time prediction of shipping noise in the Eastern Mediterranean Sea. The challenges there are twofold. One is the large number of ships. We're talking about thousands of ships traveling all the time in the Eastern Mediterranean Sea, which always change their location, of course. And second, it's the extremely large extent of the area over which the acoustic field has to be calculated and accumulated. So we started in 2013, and by 2015, 2 years later, we had developed the first version of this pilot application, which, after a number of revisions, is still operational. So you can see over here the website address where you can enter and take a look at the current situation of shipping noise. These predictions are updated every hour. So we provide predictions for the last 8 years now, every hour. And for these predictions, I forgot to say that these predictions are at various water depths. And for these predictions, we're using real-time navigation data coming from the so-called Automatic Identification System, or AIS, carried by ships. And data are provided by Marine Traffic, which is an Athens-based ship tracking service. We combine this data with typical spectral noise emission characteristics for various types of ships. Of course, we cannot know every individual ship because there are no measurements of acoustic signatures for the ships of the merchant fleet, at least. We use the etopo bathymetry. We have a quite complicated bathymetry, as you will see in a moment, in the Eastern Mediterranean Sea. And then we apply a number of simplifying assumptions, starting with the bottom. For each location, we assume the bottom modeled as an acoustic half space, as a hard acoustic half space. And the composition is the same throughout the basin. For the sound speed profile in the water column, we also assume a single sound speed profile for the whole basin, which is time varying, though, to account for seasonal change from day to day. Actually, we are updating this sound speed profile on a daily basis. And then we are applying a simple adiabatic propagation modeling, which is fine for the low frequencies we're interested in, but does not account for exchange of energy between the different propagating modes. And to cope with a large number of computations, we are pre-calculating modes on the break of each new day when the sound speed profile changes, store them, and then for each distribution, we retrieve them accordingly. Now, in the recent, so a year ago, we started considering an upgrade of this system, to improve the description of the bottom of the water column, and also to introduce a more complete propagation modeling using coupled modes to account for exchange of energy between modes. And in the following, I will very briefly touch upon these aspects to form the basis for this upgrade. Here we see the Eastern Mediterranean Sea, so the various areas are differentiated according to the slope of the bottom. So the light blue area, which is the largest part here, is characterized by mild slopes, so less than 10%. So this corresponds to a slope angle of about 6 degrees. These are mainly sedimentation areas. So this is the bottom, so to say, of the basin, or the local minima of the basin, where the sediment thickness is at its highest. So in those locations, we should apply thick sediments on top of a harder sub-bottom. The areas in yellow, over here and over there, are areas of steeper slopes, larger than 10%, okay? And here perhaps you can recognize the the Hellenic Trench, where the Eurasian plate and the African plate meet. Okay, these are steep bathymetry areas, and in those areas, sediments are harder to build up because they're washed away. So in those areas, we should apply sediments of smaller thickness. And finally, the red areas over here are areas of seamounts, where perhaps the the half space assumption is a good one. Coming to the water column, the idea is to group areas with similar characteristics for the sound speed profile. And we can do it by cluster analysis. Here we have an example of cluster analysis applied on data from the Copernicus database, 4 years of data focusing on July months. So it's the 4 Julys, so to say, from 2019 to 2022, and restricting ourselves to areas, deep water areas, so water depth higher than 500 meters. That's why you see a strange coastline here, but you can still recognize Italy, Greece, Cyprus, Crete, Heraklion, fourth. And so here we see five main groups with the different colors represented by 5 characteristic sound speed profiles on the right. There. To interpret these profiles, one should keep in mind that the speed of sound is an increasing function of temperature and pressure, and to a smaller extent of salinity. So pressure and temperature play the major role. A good way to look at this is by comparing the extreme cases, one on the west, one on the east. So the area on the west, for instance, is cluster number 5. So this is this profile over here. This one. Whereas the green area is green and purple, perhaps, is clusters 3 and 4. These are the 2 extremes. In all cases, we recognize the so-called seasonal thermocline. So in the near surface layer, we have a strong gradient towards the surface. This is due to intense warming in July. Okay, so this is due to the increasing temperature towards the surface, which plays the dominant role. Below 100 meters, we have a differentiation. So on the west here, the warming goes down to 100 meters, and then the temperature is nearly uniform for deeper layers, which means that the sound speed increases because of the increase of the pressure. So we have a linearly increasing static pressure, and that's why we have the increase, a linear increase in the sound speed from 100 to 500 meters. Whereas on the east here, where we have much warmer conditions, the heat transfer goes down, penetrates down to 500 meters. Such that, and this is throughout the year, okay? And the result is that the warming signature is felt down to 500 meters, and below, because of this, the sound speed keeps decreasing. Why? Because the temperature signal overrides that of the pressure. Okay, such observations and grouping helps us to reduce the numbers of the degrees of freedom, so to say, of the problem, and deal with this computationally cumbersome problem. Of course, this clustering is season-specific. So we've seen July data. If, for comparison, we go to January, apart from the colors, which are a bit different, and the lack of the seasonal thermocline in the upper 100 meters, similar remarks and comments apply. So here we are in winter, in the middle of winter, in January, so the near surface layer is much colder, so the sound speed close to the surface is smaller. Now, moving to the modeling part, Michael has described most of it. We are interested in low frequencies, so we are going to the Helmholtz equation. Here we have it with a source term on the right-hand side, which corresponds to a harmonic point source at a certain depth on the axis. We have boundary and interface conditions, so we have pressure release at the sea surface, so the acoustic pressure becomes zero at the surface. At the interfaces between the layers here, I have assumed a range-independent environment, so it does not change with the range. So we have continuity of pressure and vertical velocity at the interfaces, and finally we have a radiation condition which describes an outgoing wave away from the source. And as Michael presented, this is a normal mode representation of the far field in terms of modal contributions. Here we have eigenvalues and eigenfunctions. In fact, it's the real eigenvalues corresponding to the propagating modes, as Michael pointed out. And they are satisfying the vertical eigenvalue problem, the Sturm-Liouville problem resulting from the previous equations. And now if we have a range-dependent environment, remember that this is our final goal, range dependence, we can approximate this environment through a piecewise constant, so to say, approximation by splitting it into range segments, each one of which is range independent, as shown here on the right. And within each range segment, we can have a modal representation, which is written down here for one-way propagation to the right in this case. Here we still have the eigenfunctions, the local eigenfunctions now, and the excitation amplitudes are calculated in the first range segment next to the source, the same way as before for the range-independent case, and in the subsequent range segments, they are calculated by projecting, in fact, the acoustic pressure at the interface of the new range segments on the new eigenfunctions, resulting in this expression here, where we have the coupling matrix, which describes, in fact, the projection of the previous modes on the current modes. And this is the way that energy exchange between the modes can take place through the coupling matrix. Whereas in the adiabatic approximation that we initially assumed, the coupling matrix is an identity matrix, and this simplifies a lot, of course, the representation, but does not allow for energy exchange. Here's a simple comparison of results from the coupled and adiabatic approximation. You can think of this as the acoustic field, let's say, of an acoustic source, which is located here on the top left, a very shallow source, 5 meters depth, as you see over here. The frequency is 63 hertz. This is one of the frequencies of interest for the MSFD. And the sound speed profile here is representing summer conditions. It's a bilinear sound speed profile, so increase here because of the pressure effect, and then increase there towards the surface due to increase of the temperature. And we have a range independent sound speed profile, but a range dependent bathymetry. You can see the bathymetry over here, which ranges from 50 meters depth to 600 meters depth over there. And the shallowest point is here at 50 kilometers. And we see that up to this point, the two representations behave about the same. But after that, we have a big difference. This is because the adiabatic approximation already before the shallow area failed to do this energy exchange to the remaining modes. Okay? And after that, there was no energy to propagate any further. Okay, let us quickly move to the shipping noise prediction problem. As I said, the major challenges there are the large number of ships and the large extent of the area to be covered. So we are addressing this problem by introducing some tricks, so to say, to reduce the degrees of freedom. We are discretizing the bathymetry in the horizontal and in the vertical. In the vertical, typical resolution is 10 to 50 meters. We are also grouping areas with similar characteristics for the bottom, for the water column, and these results in a number of different environmental types, which are assigned to the individual points of the grid that we are interested in. And now, for each environmental type, we proceed with the solution of the vertical problem. This means we calculate eigenvalues, eigenfunctions, coupling matrices, and store them for later use. And a trick here to reduce the dimensionality of the problem is that the coupling matrices are calculated and stored only at subsequent discrete water depths. So we are not taking all possible combinations that would result in a mess of computations and very high requirements for storage, but only for subsequent discrete water depths. And then when we proceed to the calculation of the acoustic field for a certain noise source distribution, so we have a distribution of ships, what we do is we're grouping nearby ships, accumulating their intensity, and then for each grouped noise source, we define transects around the source, radial transects along which the acoustic field has to be calculated. And if there are abrupt bathymetry changes, such as the one shown here on the left, then we are introducing additional range segments by interpolation, okay? Such as to finally obtain only incremental bathymetry changes for which we have calculated our coupling matrices. And so finally we proceed to the synthesis. For the given noise source distribution, we selectively retrieve the modes, coupling matrices and everything. And here another point is that we apply mode coupling only in the cases of changing bathymetry, not in the cases of changing sound speed profile or bottom characteristics. And the idea behind that is that the major factor for the number of propagating modes is the water depth and the frequency, of course. And finally, we proceed with results, which I would like to present some typical results here. So on the left, you can see the bathymetry of the Eastern Mediterranean Sea, and the description of the bottom. On the right, you can see a typical distribution of ships. It's about 2,000 ships, or there, 2,000 noise sources that we assume at a depth of 5 meters, very shallow. Hopefully they keep that shallow if they are ships. And the spectral emission levels are taken different for the different frequencies. So we have two frequencies. These are the major frequencies of interest for the MSFD, 63 hertz and 125 hertz. These are basic central frequency of the standard 1/3 octave bands. The electrical engineers know a lot about this. So we assume an emission level at the lower frequency higher than at the higher frequency. So 165 dBs at 63 hertz, 155 dBs at 125 hertz. So at the higher frequency, we have a lower spectral level. This is typical for ships, and we keep that in mind. Here is a prediction of the noise distribution at two depths. So the top panels is 50 meters, and the lower panels are 200 meters. Okay, and at two frequencies, the 63 hertz and the 125 hertz. And this is for a winter sound speed profile, so we assume uniform temperature distribution, so only the pressure affects the sound speed profile, and this is why it is simply linear profile. Interestingly, here we don't see much difference between all these. So not much difference between the two depths, okay? And interestingly, this is a bit intriguing, not any difference between the two frequencies. Taking into account that the emission levels are 10 dBs lower at the higher frequency, this is remarkable. This is one remark that we keep. And then we move to summer conditions, simply simulated by a billionaire sound speed profile. So it's the same as before, but in the upper 100 meters, we have an increase due to temperature increase. And we see two things here. One is that we have a lower, significantly, this is the previous one, this is the new one, lower noise levels in summer for the same ship distribution. This is one thing. And another thing that the levels are even lower at the higher frequency, right, on the right, okay? So this is a summary of these remarks. So in winter, the noise levels at the higher frequency are about the same as at the lower frequency, even though the source levels are 10 dB lower. This is one thing. The other thing is the noise levels in summer are smaller than in winter, okay. And finally, in summer, the noise levels at the high frequency are lower than at the lower frequency. And this is the last slide of the presentation. We can interpret these findings by looking at the modes of the propagation. So here we see the first 5 propagating modes in summer, the top panels here, and in winter, the top panels, and in summer, the lower panels, okay? And for the two frequencies, 63 and 125 hertz. Here we have to have two things in mind. One is that due to the surface boundary condition, the modes disappear at the surface, so they have to be 0 at the surface. The surface is up here, okay? So this, the vertical axis measures depth from the surface down to 1,000 meters, okay? So at the surface, all modes disappear, as we see. And another feature of the modes is that they tend to concentrate about the so-called axial depth. This is the depth of minimum sound speed, okay? And more so as the frequency goes up. And this is what we see, for instance, here. As the frequency goes up, the modes go closer to the surface, okay? So in winter, this means that the modes at 5-meter depth, where the source is, are stronger at 125 hertz than at 63 hertz. This means that the excitation is stronger. This means a smaller transmission loss, a stronger acoustic field. So the spectral emission levels at the high frequency are lower, but they undergo a smaller transmission loss. That's why they are then comparable with the levels at 63 hertz. And then in summer, we see that since the modes concentrate about the axial depth, which is now 100 meters, okay, they're a bit away from the surface. That is, they're weaker next to the surface, which means that they're not excited as much. This explains the smaller, the lower noise levels in summer, and even more so as we go to the higher frequency. So this is the end of the presentation. I think so we now have the ingredients for the cake to start building the upgraded, so to say, and the upgraded application. And since this is the last presentation of this conference, I would like to end with some words that we were blessed with Vassilios, really blessed with Vassilios' presence for many years, and this was a precious gift to all of us, and we are grateful for that. As a matter of fact, we are missing Vassili as a bright mathematician, as an excellent and inspiring teacher, at the same time as a humble and hardworking, very much hardworking director, but most of all as a dear friend. Thank you very much.
Thank you for your lecture and for your words.
Thank you.
You will share. Are there any questions for Manolis? Clear. Since this was the conclusion of the meeting, I will say a few words on behalf of the participants, and then Babis will say a few words on behalf of the organizers. I will use plural. I'll take that liberty because I trust that what I will say reflects the feelings of all of us here. Right? So I want to thank all the people who conceived, planned, and organized the meeting, both the scientific committee and the supporting staff here. We are impressed with the quality of the organization and to the way that the whole thing was designed. I also want to thank Titina and Anastasia and Achilleas for participating, because that gave us the feeling that Vassilios was here with us as well. I feel that it was a very good choice of topics. It exhibited the breadth of the interests and contributions of Vassilios. I learned a lot myself. And beyond that, it fulfilled the mission of bringing us together. I had this, I was imagining that Vassilios was standing here, and what is he seeing? He sees his family, he sees his childhood friend, he sees his colleagues who became friends, and he sees the younger generation, his students, the students of the students, and so on. I think he would be very happy. He would be smiling the way that you can see him there on the picture smile. So thank you very much, organizers, for giving us this opportunity. We'll remember that, right? And now Babis, I think, wants to say something.
Thank you, Kostas, for your moving words. It's really I would like first of all to thank all of you that contributed to this event. This event was I would say appropriate to celebrate Vassili's life, as Titina said, and also was appropriate to ethos of Vassili's all over these years that Chrysoula pointed out in a very mathematical way, epsilon and 1 over epsilon, I think. Okay, so it's very difficult for me now, I don't know why, but I would like to say two technical things, because I think that Vassili wanted to have a scientific, inclusive, description of his legacy. And there were two things missing in this meeting. One thing is related to his essential advisor, which was Garth Baker, and his legacy. Garth Baker was a very interesting, very bright mathematician who was assistant professor at Harvard when Vassilios was a graduate student, and he worked with him. He was really influenced by him. I'm sure that he was influenced in many, many ways, and this was not mentioned enough in this meeting. Garth Baker had, despite of his very short, only 10 years, academic activity in finite elements, gave fundamental contributions. One of them is essentially he was the founder of discontinuous Galerkin methods that was later moved on in another level by Johannes Karakasian, and now I believe is, everybody agrees, is one of the accomplishments of mathematics, of modern mathematics in this century, in the sense that it's a scientific standard, an industrial standard. So I just wanted to mention Garth Baker because I remember the very long stories of Vassilios in the basement of Knossos building when he was talking for hours about Garth Baker. So I felt that I had the obligation to mention that. And the second obligation is purely scientific, that was not mentioned at all. It is related to his contribution, to Vassilios' contribution in wave propagation, numerical analysis for wave propagation. I believe this was an extremely important and seminal contribution in a series of work that laid the foundation of serious numerical methods for wave propagation in a very systematic way. And later on, he stopped working on wave problems, but many instances we heard from many talks like dispersion relations and many other things. But nevertheless, I wanted to mention these two technical issues. Okay, so I really thank you all for contributing to the success of this meeting. It was really fantastic. And I would like to finish my, I have this problem, sometimes I talk too much, by saying something about the organization of the meeting. The organizing committee was working in a very democratic way. All the decisions were taken, after thorough discussions, etc., etc. So I think that we have to be all very happy for the result. Okay, thank you very much again, all of you, and okay, that's it.